computing at the Arizona State University, where he established and heads the Make Programming Simple lab. He completed his PhD and MS in Information and Computer Science from the University of California, Irvine, and Bachelor's in Computer Science and Engineering from IIT Delhi. So his research is on making programming simple for embedded and cyber-physical systems. And as I mentioned before, many of you may know him because he has been very active at LCTES and related events. So Avidal, the floor is yours.
Thank you, Geronimo. And thank you, JJ, for inviting me here. I think it's my true honor to present at this location. So I know this is a conference on embedded systems, and I am talking about quantum computing. So this may seem like a mismatch, but you will see as we go through this this talk that actually quantum systems are inherently embedded, very resource constrained and embedded in that sense. And so we can apply a lot of our learnings and technologies to this domain. Okay, so let me start by first thanking all my co-authors here who are the real brains behind this work, and I am just the face of them. So I hope I can do justice to them, this work, and to you guys who have thankfully woken up early in the morning and come to the talk. So thanks a lot for being here. Okay, so this is the outline of my presentation, and essentially I have broken this down into two parts. The first three sections are kind of tutorial style, and so they should be really easy to follow, and the next three sections are a bit more researchy, right? So the first three sections I really want you to understand completely, and if you have any questions, please feel free to ask. This small workshop style nature of this conference allows us to be interactive, right? So please feel free to stop me anytime and ask a question. So in my mind, if we just understand the first three topics, I think we are in very good shape, right? So that would be a great achievement. So with that, let me start. So I'll start slow in with the background that most people have at least designed some ML models, right? So if you have designed even a few ML models, most probably you have made a classification model, right? So classification models are the ones that you give a dog image and cat image, and it can tell you whether it's a dog or a cat. So how do they work? So there is a neural network which is essentially just matrix multiplications and then layers of some nonlinear functions, right, like softmax or ReLU. And then the size of the input layer is equal to the size of your input. So for example, for this is for MNIST, right? So for MNIST has these images of these numbers. So they are 28 by 28 pixels. So that is 764 values. So the input layer size is 764, and the output size is equal to the number of classes that you have, right? So there will be 10 outputs. And so after this computing, you will get 10 outputs, and then we run a softmax layer on top of them. And what that does is that it takes these values and converts them into a probability distribution. So the relative ordering of the data remains the same. The higher number is still higher and lower is still lower, but they just start adding up to 1, right? And then on this we compute this cross entropy loss. This is the key for classification models, right? So the cross entropy loss is the loss function is the one that actually drives the whole training, and what does the network learn. So cross entropy loss function is actually just trying to check. So you generate 10 values, but and each value says like what is the probability that the input data is 0 or 1 or 2 or 3 to 9. So the cross entropy loss function forgets about every other output, it only looks at the output of the correct class. So if you gave a 3, right, the correct class was 3, then it looks at the output of the 3 class, and 1 minus that value is essentially the loss function. So what you want is that if your probability that if your network is predicting that the probability that this is a 3 is 0.1, that means you are very far away from truth, and what you want is that the probability should be close to 1, and then the loss is low, and then your network has learned. So essentially this is the basics of a classification model, right. So no questions till now, right. So this works well for classification, but there is a lot in terms of geometry that is left to be desired, and this is a crucial point here. So one is, if you can see at the top right diagram, cross entropy loss function, what it does is that all it is trying to do is to create boundaries between these data points, so that the data is in the right region, right. So that is one way to think about it, but actually the right way to think about it is that this cross entropy loss function is mapping data from one vector space to another vector space, and so every layer of this neural network keeps mapping to a new vector space until those points are in the right region. In fact, for a cross entropy loss function, the boundaries are already pre-decided. So if the probability is greater than 0.5, then it is that class, right. So actually the cross entropy cross function is not trying to define boundaries, it is trying to map the data to the right place, and that is what the weights mean, right. The weights are actually transforming from one vector space, mapping data from one vector space to another vector space. So I think that is clear. So the cross entropy loss function has a major limitation, that actually it only cares about moving the data to the right region. It has no concern about where the data is in the region, right. And this creates some weird problems in the sense that actually a yellow point which is from one class can be closer to a green point than to another yellow point, right, which in a sense does not make a lot of sense, because all of those yellow diamonds are one class, right. For example, number 3, while greens may be number 1. So a 3 should be closer to 3 than to 1, and this concept is actually the key of metric learning. So metric learning is, the whole idea of metric learning is that distances in the feature space should correspond to semantic similarity, and that is the key distinction that we want to achieve. And what we would like to have is a space like that on the right one. Geometrically, we would like these points to be arranged like in the right image, where the mappings of objects of the same class are close to each other and they are away from the mappings of another class. And actually this has a lot of benefits if you can do that. For example, one very strange problem of classification models is that the classification model actually divides the entire space that there is among the classes that you have defined. So if you have defined 10 classes, then entire space will be divided into these 10 regions. So now what happens is that if you give any other image, right, it will, even if it is not from one of these classes, it will map to one of these classes, right, because there is no space left. So, and what you can see is that what we want is the geometry on the right, where objects of the same class are mapped close to each other in clusters, and so there is actually space outside the clusters that is free. So if a new kind of object you give as input, then most probably it will be mapped to an empty space, and then you can detect that as a out of distribution data. So the left side is the kind of geometry that we achieve in the latent space or in the feature space by classification models, but on the right side is what we actually desire. Right, and what we desire, the fundamental key desire is that the distance between the mappings of same objects, right, should be less, and the distance between mappings of different objects should be more, in the sense that distance should reflect semantic similarity. So this key idea is called metric learning, and it is achieved by this loss function. And there are many other loss functions as well, but this is a key loss function that that achieves this this property. And you can see the first thing you can see from this loss function is that this loss function is not defined in terms of the class of an object, it's defined in terms of distances between the mappings of the objects. Right. So, distance between the mapping of x A and the mapping of x B. Right. So, how a metric learning pipeline works is that, so this this special case is this triplet learning. In this we take a data from one class x A, and then we take another data from the same class, we call it x P positive, and then we take a data from the negative class, we call x N, and we pass them through the network, and this network then maps them to a latent space, right. So, we can call them ZA, ZP and ZN, and then we calculate the distances between this ZA, ZP and ZN, and actually these x's should be z's, right. So, that is clearly wrong, but how this triplet loss function allows us to achieve that kind of clustering, you can see from here, is that so loss, so one term in this loss is distance between the A, the anchor and the positive, right. So, if this is low, then your loss will be low. If this is high, then loss is high. So, that means what this cost function or loss function wants is to reduce the distance between the anchor mapping and the positive mapping. And then the second term is m minus distance between the anchor and negative, right. So, that means you are trying to reduce increase the distance between the anchor and negative to at least m. So, if the distance is less than m, then you have a loss, but if the distance is more than m, then actually you get a negative number, m minus d is a negative number, and then your but because you are taking max with 0, so then your loss becomes 0. So, this causes a pull and push effect where the mappings of the same class get clustered together, and they are clustered away from objects of different class. And this fundamental rule that the distance between the mappings reflect the semantic similarity works both inside a cluster as well as outside the cluster. So, you can say that the green objects are more similar to the red objects rather than the blue objects, right. And in practice it would be like the mappings of cats is closer to the mappings of dogs than to mappings of elephants, right. So, okay, so we want to do metric learning. So, how do we do this? What is the requirement to do metric learning? So, let us go back to classification problem first. So, in classification problem, if you want to solve the optimization, then you need to work in vector spaces. Why vector space? Because vector space means that every element is a vector, and you are allowed to subtract these vectors and also multiply them by a constant scalar. So, you will need that to compute, to do the gradient descent, right? Otherwise, you cannot compute Wt plus 1 minus Wt, right? And you cannot multiply by a scalar the eta, the learning parameter. So, to be able to do this, you need this to be a vector space. But that is not enough. We also need it to be continuously differentiable, in the sense that at all places you should be able to differentiate the loss function with respect to the weights. So, this kind of a space is a continuously differentiable vector space. Now, by definition, this vector space does not have a definition of distance. So, definition of distance comes from metric spaces, and that is why this name of deep metric learning, the metric comes from this definition of metric spaces, which is essentially a set where there is a definition of distance. And there can be many definitions of distance, many are allowed. The only requirements for a definition of distance is that distance should always be positive, and if you take a vector and multiply it by a scalar, the length of that vector is equal to the absolute value of the scalar times the length of that vector. And it should follow the triangle inequality. The triangle inequality is the one that actually gives space to structure to the manifold of the data, because what it says is that the shortest distance, the straight line distance, is always the shortest. So, Zi plus Zj will always be less than the length of Zi and length of Zj. So, you can think of this acting in terms of that if you have two red dots and a blue dot, and the blue dot is farther away from the red dots, right. So, let us say it is at least m distance away from the red dots. Then what this triangle inequality does is that it creates a circle in 2D space, it creates a circle around this red dot of m radius, and the blue dot can only exist outside this circle, right, while another red dot could be closer. So, essentially this triangle inequality is super important, and it creates the structure in the space. Okay. Next point. So, before we formally define the requirements of what is required for metric learning, one very important part is that is the need or mandate for high dimensions, and this comes from this Covers theorem, and it is actually very intuitively explained by this experiment at the top. So, what this is that you have a 2D space, and you have these green points and these red points, and this is very classical data set, it is called concentric circles. So, in this two-dimensional data, if you want to classify them, that means you need a one-dimensional line, right, to separate them. But there is no one-dimensional boundary that you can create that will classify this data correctly. So, what Covers theorem says is that it becomes easier to classify if you project this data in a higher dimension, right. So, what we do is create another z axis, and the z coordinate of every point is equal to the radius, the distance from the center of that point. So, if you can map it, this 2D data, into 3D, then you can very easily now create a horizontal plane, and all points below this are green and all points above this are red. And essentially that is what this Covers theorem is saying, that it becomes easier and easier to classify data or find a separating boundary if you project the data in higher dimensions. So, this is key. So, coming back to what are the requirements for metric learning. So, metric learning, what you want is higher number of dimensions. The higher number of dimensions you can have, the better the separability of the data you can achieve. You want a distance metric, right, and because as you saw, the loss function actually contains distances, right. So, you have to calculate the loss, you have to calculate distances, and it is a function of distances. So, if you can have a quick way to calculate distances, that would be great. and third is that it must be differentiable everywhere. Right. So, these are the key requirements for metric learning, and metric learning is now the cornerstone of all ML technologies. So, for example, the word2vec, clip, right, all of these are already pre-designed metric learning models and actually mappings that that generative AI is built on. Right. So, this part, to conclude this part, as in this is classification models are good, but they do not enforce very good geometry on the latent space. So, the geometry that we desired can come from metric learning models, but metric learning needs a distance function, and so it needs a continuously differentiable normed vector space. And so, what you would desire for good metric learning is high number of dimensions, continuous differentiability, and a native or quick distance calculation function. Right. So, this finishes the first part of my talk, which took double the time that I thought. Okay. But I hope this part is clear, right, to everyone. So, then no questions. Okay. So, now let me delve a bit into quantum geometry, the promise of quantum geometry. So, the whole point of this section is that I am trying to show you that quantum geometry actually provides very good solutions to all the three requirements of a good metric learning approach. So, it gives you very high number of dimensions, it has a native distance calculation metric, and it is continuously differentiable. So, that is the goal we want to reach after the end of this section of the talk, right, because those are the three desires for good metric learning approach. So, this is where we are trying to reach. Okay. So, let us start simple again. What is a qubit, right? So, and to understand that, let us backtrack one more step. What is a bit? So, bit is a piece of information and it can be in state 0 and 1. Most crucially, you can think of an internal state of a bit and external state of the bit. So, externally when you read a bit, it is, you will read it as either 0 or 1. An internal state of the bit is same as the external state of the bit. So, if the internal state is 0, you read 0. If the internal state is 1, you read 1. A qubit is different in the sense that its internal state is different from the external state. So, internal state of a qubit is a 2 cross 1 vector of complex numbers. So, it is alpha beta, where alpha and beta are both complex numbers, with a limitation that alpha square plus beta square is equal to 1. So, what is alpha square? Alpha square means, where alpha is a complex number, alpha square means alpha times alpha star, which alpha star is the complex conjugate of alpha, right. And so, then you can say that if A, and what is complex conjugate? So, if alpha is A plus IB, then alpha complex conjugate is A minus IB, and then you can see that alpha star alpha is A square plus B square, which is a positive real number, right. So, so alpha square of a complex number is always a positive real number. Okay. So, the internal state of a qubit is actually very, very rich. It is not just binary 0 or 1, it is 2 complex numbers. So, one can be 3 plus 2i, another can be 4 plus 6i, right, as long as they follow the normalization constraint. But you can see it is 2 complex number, each complex number is comprised of 2 real numbers. So, there are 4 real numbers inside a qubit state. So, it can have infinite possibilities. I mean, even one real number can have infinite possibilities, but these are 4 real numbers. So, there are it is a very rich state, but the challenge is that whenever you read it, you will read it as either 0 or 1, right. So, the external state is still very limited, while the internal state is very rich. Okay. So, we understand that qubit is a 2 cross 1 vector, and like any vector space, there is a basis of that vector space. So, the simplest basis of this vector space is this 1 0, and that other one should be 0 1, right, 1 0 and 0 1. And then you can see that any vector in this vector space can be represented as a linear combination of the basis states, right. And in quantum computing, this Dirac notation is very popular, and actually once you get used to it, you realize it's brilliant in terms of when you are operating with vectors. So, it's very easy. This is a weird symbol which is, so this is called the ket of 0, and this is a column vector 1 0, and ket of 1 is 0 1, and we write an arbitrary state like alpha beta as a ket of psi, which is equal to alpha times 0 plus beta times 1, right. So, you can see that, so this ket of 0 and ket of 1 are the basis vectors, and you can represent any general vector as a linear combination of these basis vectors, except that the coefficients of the linear combination can be complex numbers, right. So, that is a bit of a complexity. So, then along with this ket, we also have a bra notation. So, bra of psi is actually the conjugate transpose of the ket vector. So, alpha, so this psi was a 2 cross 1 vector alpha beta. So, so we need to take conjugate transpose. So, first transpose it, so it becomes a 1 cross 2 vector, and then you conjugate it, so it becomes alpha star beta star, right. So, a row vector of alpha star beta star. And then what you can easily see is that if you multiply these two together, right, with bra first and ket later, then that comes out to alpha star beta star times alpha beta, and that is alpha star alpha plus beta star beta is equal to 1, which is the same as the normalization constraint at the top. Right. Okay. So, where are we? So, we understood that the states of a qubit are a 2 cross 1 complex vector, right. So, if you think about it, it is a 2 cross 1 complex number. Each complex number is made up of 2 real numbers. So, that means there are 4 real numbers, and there should be 4 degrees of freedom, right. But actually, because of normalization constraint, 1 degree of freedom goes away, and there is a unique property of quantum systems where a state and a scalar multiple of the state actually means the same thing. So, a state psi times is the same as another scalar constant c times psi, right. So, that because of that you lose another degree of freedom. So, essentially what it comes, so that means there are only 2 degrees of freedom left. That means that this this state of a qubit is a surface, right. So, actually it is a surface, all the states reside at the on the surface of a unit sphere, right. And you can write a general state as in this form, cos of theta by 2 0, ket 0, and e to the power I phi sin theta by 2 ket 1. Why? Because as you can see this in 2 ways, right. One is that this cos theta by 2 is the so 0 and 1 are the basis vectors, and cos theta by 2 is the coefficient of 0, and e to the power I phi sin theta by 2 is the coefficient of 1. So, this is a linear combination of 0 and 1, right. And you can also see that actually that because this is a point on this unit sphere, right. So, so the coefficient of 0 can be cos theta by 2 and the coefficient of 1 can be sin theta by 2, so that when you square this it will become 1, right. So, that cos square theta by 2 and plus sin square theta by 2 will be equal to 1. Okay. So, the point is that that all the qubits live on the sphere, on the surface of a unit sphere, and their general state can be written as this. So, most crucially, theta can have a range from 0 to pi, and what is theta? Theta is the polar angle, right. So, the angle from the z axis, and phi is the angle from the x axis. So, theta can have a range from 0 to pi and phi can go around the entire x y plane, right. And by choosing any value of theta and phi, you can access any point in this block sphere, right. Okay. So, this makes sense. Now, so this is a vector space, and now we need a metric of distance here, right. So, how do we get a metric of distance here? So, actually there is an inner product that is defined on this space, because this is actually the qubit state is not only an inner space, but actually it is a Hilbert space, and there is one more step that I skipped. It is actually a projective Hilbert space, but let us not go into that complexity. But in an inner space there is an inner product that is defined, and inner product of two vectors psi and phi is actually the bra of one vector times the ket of another vector. So, you can calculate it like this, and then you can see that the inner product of a vector with itself is always 1, right. This is we saw this in the last slide. What it means is that the length of all vectors is 1, right, and that is why they are all reside on the surface of a block sphere. So, then but using this inner product, we can define a fidelity function, which is actually this inner product square, and that gives us also an definition of angle between two states or fidelity between two states. Fidelity, but by the nature of this, actually fidelity is opposite of distance, in the sense if the fidelity between, if you take the, if the states are same psi and phi, then fidelity will be 1, and if the states are orthogonal, then the fidelity will be 0, because that is how cos alpha works. So, we can actually define a distance metric by subtracting it from 1 by reversing that function, and essentially with this distance function, which is defined using fidelity, distance between similar states is less and distance between different states is more, right, and the distance is in the range of 0 to 1, that is it. So, this gives us a distance metric. Okay. The next, so we now know that the qubits are the qubit states are actually vectors, right, on a unit sphere. So, now what do quantum operators do? Quantum operators actually just change the state. So, they rotate the state. So, you can think of all the gates just in terms of these three fundamental gates: Rx gate, Ry gate and Rz gate. Rx gate rotates the state around the x axis, Ry gate rotates the state around y axis, and Rz gate rotates the state around z axis. So, there are many more gates and all that, but you can think of all that the gates do is just rotate the states, and you can rotate from anywhere to anywhere using just these three gates. In fact, actually you can rotate with just two of these three gates, you can pick any two, right. Okay. And another thing that I want you to see is that, so what are these gates? These gates are actually just matrices, right. So, and how do you apply, so our vectors were 2 cross 1 vector. So, these gates, quantum gates are 2 cross 2 matrices, and how do you apply a gate to a state? You multiply it from the left. So, So essentially, where is the pointer? Here it is. Yeah. So if this U is the gate, which is a 2 cross 2 vector, and psi is your state, then you multiply U from the left, and that gives you the new state psi prime, right? And there are some restrictions that not any matrix can be a gate. Only unitary matrices are allowed, and what it means is that there are two big implications of that. Unitary matrices mean that U dagger should be identity. Again, dagger, what is dagger operation? Dagger is transpose conjugate. So you take a matrix, you take its transpose, right? So make rows into columns and columns into rows, and then take the conjugate. So that's the, so that means take complex conjugate of each number. So that's how you get U dagger, and U times U dagger should be identity. So the two implications of this being a unitary matrix is that, one, that it preserves the length of a vector. So when you apply U to psi, you get psi prime. The length of psi prime is same as the length of psi, right? And this is very useful because our states were unit vectors, right? Vectors of length 1. So after applying any gate, they still remain a vector of length 1. So that means the state is still on the surface of the block sphere. Then second property that it has is that it is angle preserving. That means if you have two vectors, you apply U on them, then they both rotate together. So it preserves the angles between them, right? Okay, so this is one very important property, that quantum operators only do rotation, and they do like a solid rotation. They don't rotate different vectors by different amounts, they rotate everything by the same amount, right? Then second important thing is that all quantum gates are infinitely differentiable. So a quantum gate like this Rx gate is written in terms of sin theta and cos theta, and you can differentiate it. Sin theta will become cos theta will become minus sin theta, and you can keep differentiating it indefinitely, right? So this satisfies our important property that we want a continuously differentiable loss landscape, right? Okay. Now this is another slide which says how do we measure. So this is actually fascinating. So the what we saw is that the defining property of quantum of qubits is that the internal state is very rich. It's made up of two complex numbers, but externally it is binary, right? So how do we achieve that? By math, right? So what happens is that all the measurement operators are actually Hermitian matrices. So when you have to measure a state, you can only measure it by a Hermitian matrix. So what is a Hermitian matrix? Hermitian matrix is one in which H is equal to H dagger, right? So again, what is the dagger operation? Is the transpose conjugate or conjugate transpose. So first you take the transpose of the matrix and then conjugate every element. So if a matrix has to be the same as its transpose conjugate, that means at least its diagonal should be real numbers, right? And it should be a symmetric matrix. So this is one property of Hermitian operators, Hermitian observables. Okay. Now how do we measure? So if we take an operator and we give it a state, say psi. So we have an operator here z, and we get a state psi. Then the only values you can observe are the eigenvalues of this Hermitian operator. So in specific, this observable z is 1 0 and 0 1, 0 minus 1. Its eigenvalues are 1 and minus 1. So the only things that you can observe when you read any state, whatever be alpha beta, right, whatever be psi, you can only read 1 and minus 1. And when we talk in computing, we actually convert this to 0 and 1. 1 is converted to 0 And when we say state 0, that actually means that we read 1, and when we read -1, then we say it is state 1, right. So, but that is just the binary issue. Okay. Now, the other property of quantum mechanics is that as soon as you read measure a state, right, that state collapses to the corresponding eigenstate. So, for example, so now we can understand the whole measurement process. So, the observable is Z, its eigenvalue is 1 and -1, the corresponding eigenstate of 1 is 1 0 or 0, and the corresponding eigenstate of -1 is 0 1 or 1, right. So, if you get a state alpha beta and you read it, you can only read one of these two values, either 1 or 0. If you read a 1, the state will collapse to 1 0 or the 0 ket 0, and if you read -1, the state will collapse to 0 1. So, the state, so measurement is destructive in the sense, right. So, it changes the state. Now, so you can read these two values and it is statistical in nature, right. So, what do you read? So, you can read 1 or -1, but with what probabilities? So, you will read 1 with the probability of alpha square, and you will read -1 with the probability of beta square. So, essentially to calculate that, we calculate the fidelity. So, the probability of reading one of the eigenvalues is a measure of fidelity of that, of your incoming state with the eigenstate, right. So, you can see that measurement actually evaluates the fidelity, right. So, the probability with which you will read 1 is equal to the fidelity of the two states. One of them is your input state and other one is the eigenstate. So, this again this is again towards our property that we want a matrix, we want a system in which the fidelity or distance can be measured natively. Then this is probably the most fascinating aspect of quantum spaces, quantum geometry. So, so what does the state of a multi-qubit system look like? So, we saw that a state of 1 qubit can be represented by a 2 cross 1 complex vector, right. So, to figure out the state of a 2 qubits, we actually calculate the Kronecker product of the two states. So, which is the second vector is multiplied by each element of the vector. So, you can see that in operation, and then you get a 4 cross 1 complex vector, right. So, and so what you can see is that so for a 1 qubit system you have 2 cross 1 complex vector. For a 2 qubit system you would have a 4 cross 1 complex vector. For a 3 qubit system you would have a 8 cross 1 complex vector, and so for a n qubit system you have a 2 to the power n cross 1 complex vector. So, that means the dimensionality of your space is increasing exponentially with n. So, you have 10 with 10 qubits you get a vector of 1024 complex numbers, right, and with 50 qubits you can have a state which has dimensions which are larger than the number of atoms in the universe, right. So, the dimensionality increases exponentially. So, this is, so we fulfill all the 3 promises of what we want in a very good metric space, right. Quantum space provides exponential dimensionality, it provides a native distance engine, because whenever you measure the probability of measuring a 1 is a measure of the fidelity, right, and it is infinite, all the operators are infinitely differentiable. So, you can calculate your loss everywhere in the landscape. Okay, this is a good time to stop. So, any questions, because these two are kind of heavy things, although they look simple. Any questions? No? Okay, so clearly we can't finish the whole talk today. So, we will just do one more section and then stop there. right? And I think which is also very instructive. As I said, I mean, if we can just cover the first 3 sections, that would be great, right? Yes, please. Yeah, so distance is, I already showed that equation. This is the distance between 2 states. This, that's a very good point. So, actually, for a metric space does not define a distance metric, it only requires a distance metric, and any distance metric is okay as long as it satisfies 3 properties. One, that the distance is always positive. Second is that scalar multiply works, right? And third is the triangle inequality. Any distance metric that satisfies these 3 properties can be used for metric learning. And this is just one of the distance metrics. There can be many others. Perfect. Thank you for a good question. Okay. So, now the only other section that we will go over is how can we now create a quantum metric learning architecture, right? So, this is also just the basics of how we can do this. So, we will start from a naive approach, what an ML engineer would start doing, and then see what are the problems in that and see if we can solve them. Okay. So, in my mind, if I were an ML engineer, not an expert ML engineer, just a beginner ML engineer, then this is how I would design a quantum metric learning pipeline. So, I will take the input data, but input data like this MNIST image is classical, right. So, I need to convert it into a quantum state, right. So, that is the first step, data encoding. Then second step would be to create a parameterized circuit, right. So, parameterized circuit with parameters theta that we can train, right, and improve the separability of the data, right. And then we need a way to measure the distance, right, and then using those distances we will calculate the loss, and then from that loss then we can calculate the gradients, right, del L by del theta, right, and then update the parameters theta, right. Does this make sense? This is how you would make a metric learning pipeline. So, let us go into each stage and see what are the challenges and what we need to fix. So, first is how do we do data encoding, right. So, actually we can use the rotation gates that we have, right. Rotation gates take a parameter theta, how much to rotate, right. So, you can rotate by that. So, typically we draw quantum circuits from left to right, where left is the input, then there is a gate, and then the parameters come from the top, and then the output is on the right side. So, we can use this RY gate for example, or RZ gate or RX gate, whichever gate rotation gate you want. This will rotate and create a state, and that state will be data dependent because it is xi is the parameter. The only challenge here is that the rotations have periodic nature, right. So, if you are rotating, for example, if this was the RY gate, then theta can only go from 0 to pi. So, that means you must scale all your data to be between 0 and pi, and then you can create unique states for all your data, right. Does that make sense? So, no problem here. I think this is pretty straightforward. Okay. Second, so now we need a parameterized circuit. So, now we have encoded this data, and we need a parameterized circuit that will increase the separability as we train this theta, as we pick this theta. So, here there is a fundamental problem. Actually, whatever theta you pick, we saw that actually quantum gates are like rigid rotations, they cannot change the angles between the data points. So, actually this parameterized circuit will never work. Whatever is the separation between the data will remain the separation between the data. It can rotate and all that, but it cannot change the separation. So, to separate the data, we use a data reuploading ansatz. So, ansatz is just a fancy name quantum computer people use for describing a circuit. So, essentially it is a circuit, right. And it is data reuploading in the sense that, so there is a layer that is the parameterized layer, and then there is a data layer. So, there is some gates. So, you again rotate using the x parameters, so your inputs. So, by alternating this parameterized theta parameterized gates and data parameterized gate, you can actually achieve separation of data. JJ. Yes. Yes. Right. So, we are doing metric learning, right. What we want is that the data comes in, we want to separate them, right. So, you can think of it as, I think it may be this, yeah. So, I am getting say maybe zeros and ones, let us just think of binary, right, 0 and 1, then zeros and ones get encoded on this block sphere. If I have trained it correctly, then all the zeros should come at the top and 1 should come at the bottom. So, I want to increase the separability of the data, right. But if I do not have data dependent gates, then you cannot change the separability, they all move together. So, how does data dependent gates actually enable separation? You can think of it like this. So, for example, your data is 10 and 20 in very simple terms, degrees, right. So, the so the 10 one will rotate by 10 degrees, 21 will rotate by 20 degrees, right. Now in the next step, when you do it again, then again the 10 one will rotate 10 more degrees, so it will go to 20 degrees, but the 21 will rotate 20 more degrees and go to 40 degrees. So, now the separation is doubled. So, by interleaving these quantum parameters and data dependent layers, you can actually change the increase the separability. Okay, only 5 more slides left. Yes. They are quantum gates, they are just rotation gates, but they are parameterized by data rather than parameterized by trainable parameters, right. So, let me go back here again. So, you can see, so our layers are formed of W layers and V layers. W layers are parameterized by the trainable parameters theta, right, and X layers are parameterized by the data. So, that is why this is called data reuploading. Okay. Then our next part, and this is where it gets more interesting. So, our next part is that we need to calculate distances and we need to calculate loss, right. Okay. So, we said that distance in this quantum geometry is the metric we are using is the fidelity, right. And so, when we measure the probability of you read only 1 and minus 1, the probability of reading a 1 is a measure of the fidelity. But the problem is that you cannot do one measurement and find out this probability. Finding out this probability is a statistical exercise. So, you need to do several experiments, imagine like doing 100 experiments, and then you see that 70 times you get 1 and 30 times you get minus 1, and then you will say, oh, probability of getting a 1 is 70%, and then you can say, okay, that is a measure of the fidelity between the two states, right. So, that is the challenge, and you have to do several shots of this execution, typically more than 1000, between 1000 and 10,000 shots you have to do, and then you calculate the number of experiments when the output was 0 and divided by the total number of experiments, that is your measure of fidelity. right. So, I am overlooking a couple of things. For example, when we do a measurement, you calculate the fidelity between one of the eigenstates of the observable and your given state. So, there is a swap test circuit that you can make, and we can discuss this offline, but essentially what it does is that given any two states, it projects the fidelity between these two states to the probability of you reading a 0 in the first qubit, right. So, all you need to do is to make several observations and see how many times the first qubit is 0, right, and that is your measure of fidelity between the two states. But so now you have to do these shots, right. But once you compute the fidelity, you can compute the loss function pretty straightforward, right. Except you can see that in this I changed the signs of AN and AP, fidelity of AN and AP, because fidelity is inverse of distance. So, this is the correct formula. Okay. Then gradient calculation, right. So, how do we calculate gradients here? So, the problem is that yes, the gates are infinitely differentiable, but you cannot access the state inside the quantum computer. At the end of the day, you give this input x as the input, and all you read is when you do the measurement, you can read what is the output state, right. So, you cannot do back propagation as we do in classical computers. But fortunately, there is actually a simple way to calculate the gradient, calculate the exact gradient delta L by delta J by calculating the loss at the parameter plus pi by 2 and loss at parameter minus pi by 2 and divide by 2. And intuitively why this works is because any loss function can be actually written in terms of cos theta and sin theta, and so you can see that derivative of this is the cos is replaced by sin and sin is replaced by cos, and by doing theta plus pi by 2 and minus pi by 2 also does the same thing. So, you can calculate that function using these two functions, right. So, now to calculate the gradient, you need to do two experiments. Run this circuit with parameter theta j plus pi by 2 and parameter theta j minus pi by 2. So, this increases 2 more shots, and now these two effects are multiplied with each other, right. So, this is the final QMEL flow that would actually work, right, and give results. So, essentially we take the data, we scale that data, we use the rotation gates to encode that data, then we have a learnable circuit which is a data re-uploading circuit, and we run this for every pair of XA and XP and XA and XN, and for each parameter theta j, right, we have to run this, and for each parameter we have to run theta j plus pi by 2 and theta j minus pi by 2 and do the swap test here, and then collect the number of zeros that you get in the first qubit, and that gives you the measure of fidelity between the encoded states of these two, and that you can use to calculate the the gradients, and then you can update the parameters. Okay. So, this is extremely compute intensive, right. This requires 4 into p into n shots to do one step of gradient update. So, very, very bad, right. So, n shots is about 1000, and then p is the number of parameters that you have, and 4 is because you have to do 2 times for each one, and then you have to do for XA and XP and XA and XN. So, I will stop here. So, hopefully, what you got is a insight of what is needed for good metric learning, why quantum geometry provides a very good geometry for quantum metric learning, but there are many issues if you just want to do it directly. So, actually the work that we have done enables us to do quantum metric learning without falling into any of these traps. So, we did not have time to go into the solution, but you can read our paper, and but hopefully you can you reached here.
Yeah, thanks, Avida. So we still have time for some questions, some further questions.
I don't know whether you make this a bit limited to the content metric, metric learning, because it looks to me that original problems are relevant to clustering and also other partitioning problems of the data, right? So is that on purpose, or you somehow try to focus only in this talk based on that?
No, I think we don't realize, but actually all AI is almost, metric learning is a very big part of AI. So, metric learning is very important by itself, even though we start learning from classification models, the real learning is in metric learning. So, so that is why.
Very good talk. I was very interested in this, the quantum computing. I'm kind of new to this topic, by the way. I was really looking forward to hearing more about your research outcome. So can you just deliver more the sentences?
So actually, let me give you some highlights of our results. So actually, there is a quantum metric learning tutorial on Google Circ, because Google makes a quantum computer and they have a programming language to actually program that quantum computer, that is called Circ. So there they do actually metric learning with 2 by 2 images. So they just 2 by 2 image, just 4 pixels, right, because this does not scale. In contrast to that, our approach, actually we can do complete MNIST, we can do omniglot, we can do multimodal learning. All of this is enabled because we figured out a way to learn in quantum Hilbert space while avoiding all these pitfalls. So I think the biggest contribution of this work is in scaling quantum metric learning to realistic problems. It is not still comparable to classical learning. So that is not the approach. I think classical metric learning is very advanced, and we are still learning how to do quantum metric learning. And if you look at all the papers that are there in quantum machine learning field, they all use very limited data sets, like the concentric circles data set or binary data sets and so on. So one of our biggest contributions is that we have been able to scale it up to at least realistic levels of problems.
Right. I had a similar question, maybe for us to get a sense of how you do this first encoding. So you gain the dimensionality because of the qubits, right? So the amount of qubits gives you a space of 2 to the n, right? But then you start with an image like this one right here, MNIST, maybe with 256 bits, right? So an 8 by 8 image. So you have 256 bits in the image.
So this has 28 cross 28, right? 764.
All right, 28 times 28, that's classical bits.
Yes.
But I guess you have to reduce it into qubits. So actually you reduce the dimensionality into the qubit encoding. Can you say more or less how is this scaling more or less working? So
actually this ultimately in our solution, these images can be converted into 6 qubits.
6, okay.
So they can be, their state can be expressed in 6 qubits. Actually, if you think about it, qubit can hold a lot of information.
Yeah.
1 qubit could actually encode everything, right? Yeah. Because it has infinite possible states.
Yeah.
But yeah, I think the separation and your accuracy of measurement and all that come into
Right,
play.
because I was wondering about like the scalability, and yeah, with 6
Yeah.
qubits, I mean, you can imagine a quantum
Yeah.
computer with 6 qubits.
Correct.
And then maybe final question, if nobody else. So then you have to do all these rotations, and I guess there's going to be some physical constraints in the granularity at which you can do these rotations. Is that a problem at all or not? Or
So that's actually a very important constraint, and this is, I think, all embedded people can relate to, is that quantum computers, as you know, they have very few qubits, right? So even the best quantum computer has only 50 usable qubits for now, right? And their circuits cannot be very deep because there is noise and decoherence that happens. So you must compute in a very shallow circuit. So in fact, our encoding and the whole quantum circuit is just 2 gates in
Okay.
our solution. So that's a very important part of our solution.
right. So we're 1 minute over time, but if somebody else has another question, otherwise, let's thank Aviral again. Oh, too late. Offline. Let's thank Aviral again. Thanks.
Thank you.
Yeah, I know who's giving the talk. Yeah.
Approach.
I'm just trying to locate the third. If either of the authors of the third paper today is around, just identify yourself. Are you the Hikami? Are you going to be? No. No. It's, okay. Yeah, I'm locating the present. Yeah, someone. This will be terrible if. Pardon? The mic. There's a mic which we'll mic you up, right? Yeah.
All right, no rush.
I should. Do you want to check if? You want to quickly check if your
we
slides-
checked.
You did. You did. Did you check if your things project?
Oh,
Yeah. I think you could quickly do a check.
shouldn't be a problem, but
Yeah. Shouldn't be a problem. Oh, you're going to be the speaker? Okay.
Yes.
All right. So. Just do a quick check.
Okay.
In the next couple of minutes.
Yes.
That is. Compiled to efficient and readable C code by Clément Chavanon and others, mainly from INRIA, ERISA, blah, 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 and from KTH. It's like four affiliations. Over to you, Clément.
Thank you for the introduction. Is the mic working? Yeah, okay, thanks. So here, hello everyone, I'm Clemens and I'm going to present work on a domain-specific language. Yeah, domain-specific language that is aims at facilitating the verification of system code and that is compiled to both efficient and readable C programs. So this is a joint work between INRIA and KTH. So the motivation behind this work is that verifying system code is challenging because those programs are written in low-level languages such as C, for example. So you have to reason with pointer-based semantics, and you have to maintain complex memory invariants when you reason about those programs. So what we usually do when we want to verify system code is to work with higher level abstractions. For example, using a refinement approach in which we are going to define several models of the system at different abstraction levels, and we are going to do refinement proofs within those models, which means that for a given model, we are going to prove that it is a valid implementation of the higher level abstract model. And we have wonderful tools to do that mechanically nowadays, which are proof assistants, that are tools to that have a programming and a specific encryption language that are used to reason about programs. However, when we use this approach, there is a semantic gap between the very high-level abstract model and the source code that we would like to run on the hardware. So in this work, we took the approach of a compilation to automatically derive source code from abstract model. And the ultimate goal is to have a verified compiler. So this means that we want to check that the compiler does not introduce bugs when it compiles to source code. And more specifically, in our cases, we want to start from ROC programs. So ROC is one of those proof assistants. And we want to generate C code, but not any type of C code. C programs that are suitable for embedded systems means that fit the constraints of those systems, memory-wise and time-wise. So ROC, the semantic gap between ROC and C is that ROC is a very high-level programming language, purely functional. So it means that there is only constant values, and it has to be executed under runtime, so it's not suitable for embedded systems. So that's why we come with our own domain-specific language, which is called Baroque, which is still purely functional but very minimal. And it can be seen as a ROC subset with a particular programming discipline that I will talk about in a few slides. So to achieve certain efficiency, we compile with in-place updates. So basically, we did not do copy when we compile to the C code, but values in the C programs are mutable, and so that's what we call in-place updates. We also made a very pragmatic choice to compile to readable C code, because our goal is to bring those tools to the system programmers community. So we think that it's important to generate C code that can be reviewed or easily debugged by system programmers. Finally, because system code requires fine-grained control over the memory layouts, we have some annotation in the language that allow to control these layouts. And as a proof of concept, we implemented the S3K separation channel, which was originally created at KTH. So there is already successful stories in the literature that are using a compilation to implement system codes, for example, Lostar for cryptographic algorithms and Cogent for file systems. And what we wanted to do with Baroque is to kind of having a compromise between those two works, so have a lightweight approach so that the language is minimal and easy to learn, and having the possibility to generate idiomatic C and readable C code for the reasons I mentioned in the previous slides. And also we needed some features such as arrays, and more specifically arrays of non-primitive values that were not supported by Cogent, for example. So the rest of this talk is divided in two main parts. The main part will talk about the Baroque language and its compiler. And the second part will talk about the Baroque part of this microkernel called S3K. So I will not talk about proof in this talk. So to give an overview about the compilation architecture of Baroque, the first step is to compile the functional language Baroque into an imperative one called imp1. So the compilation process is divided into multiple phases to ease the proof of correctness of this compilation. And the first three passes are inspired by a work of Bowman published at Uppsala 2 years ago. Because combining functional programs with in-place updates is incorrect for the majority of functional programs, we have to check that for a given program it's actually correct. So we have this static analysis that is performed on imp1 that does this check. And we finally introduce another intermediate representation on which we perform some optimizations to make the code more readable and idiomatic. So those optimizations are copy propagation and globalization. So globalization is the fact of replacing some function parameters by global mutable variables. And sorry, finally, we generate C. There's one slide missing here, sorry. So it's very, oh. Yeah, sorry, there is a bug in the slide. So I'm going to talk about a little more of the language with an example. So this is the implementation in Baroque of buffers. So we have a record type buffer with, which define the length of buffers and the contents. So the brackets here are used for declaring an array of 64 unsigned integers. And then we define the buffer write function that writes a value v into the buffer b. So basically this function first checks that the buffer is full. If it's the case, it does nothing and just return the buffer. And if the buffer is not full, it writes the value v at index length of the buffer content. So to give you an idea of how the static analysis works, I would like to run a concrete execution of this program with the following inputs in the two semantics. So in the copy semantics, in which we only do copy, and in the in-place semantics, in which we do in-place updates, which is the semantics that the compiled C code have. So in the copy semantics, the buffer B is associated with buffer value. So just a functional value, but in the in-place semantics, we introduce a memory. So the buffer B is a pointer to a buffer record, and the buffer content is a pointer to an array of unsigned integers. So when we execute the first expression, so we read the contents, b.contents, and put this in a variable ct. So in the copy semantics, we do a copy of the buffer content. But in the in-place semantics, what we do is that we have a pointer that is an alias to the buffer, the input buffer content. And when we do an update in the copy semantics, again, we copy the content of CT and put it into CT1, and we update the value at index 2, and we put the value 7. But in the in-place semantics, what we do is that we directly mutate the memory. So we replace 0 here by 7. And CT1 is also a pointer and is an alias to CT and points to the buffer content. I can continue to execute this program. And at the end, we obtain those two final states. So in the copy semantics, there are all of these local variables that were copied from each other. But in the in-place semantics, B1 and BRES are aliases to the input buffer, and as I said previously, CT and CT1 are aliases to the input buffer content. So if we look closely at the two states, we can see that some memory access path evaluates this, differently in the two semantics. So for example, b.flanks evaluates to 0 in the copy semantics, but it evaluates to 3 in the in-place semantics because we did in-place updates. So the static analysis tries to compute those invalid paths, and then it checks that in the return value, so here it's the return buffer BRES, everything is coherent in the two semantics. So in this example, this is the case. So the length and the content of the buffer are the same in the copy and in the in-place semantics. So we say that in the in-place semantics, the program behaves the same as in the copy semantics, and we accept the program. However, let's say that we made a mistake when programming this function, and instead of b1.length, we wrote b.length. So in this case, it means that the result buffer here will not contain the updated content because it was contained in b1. So if we execute this new version of buffer write, we obtain this final state. And what we can see here is that in the copy semantics, the value has not been updated here, but in the in-place semantics, because we do in-place updates, it has been updated. So this memory path that has as origin bres does not evaluate the same in the two semantics, and we reject this program. So to summarize how the static analysis works, basically for a given function, and assuming that all of the arguments are valid, the static analysis will compute this set of invalid paths that catches the incoherence between the two semantics, and then it checks that the return value is associated with any of invalid path. If it is not the case, then we can accept the program. So we can informally replace what the static analysis enforces with this following programming discipline, which is always use the most up-to-date memory path to access a value. Okay, so now let's see how this program is compiled to C. So I put again the definition of buffers in Baroque. And the associated C type is the following. So Baroque records are compiled to C buffers and C strict, sorry. And the contents of the buffer becomes a pointer to an array of unsigned 64-bit integers. And as in the example before, the memory layout of this unallocated buffer is the following one, with content being a pointer to an array. If we do not want, if we want to remove this indirection here, we can use what we call an unboxing operator, which is the sharp operator here, which say, okay, let's remove this pointer and flatten the buffer content inside the buffer record. And as we also need to specify the length of the array so that it can be compiled to C. And the memory layout of this new type is the following. So everything is just flattened, and we do not have indirections anymore. OK, so now let's see how we compile the buffer write function. I highlight here the lines that correspond in the Baroque codes and in the C code. So what we can see is that some assignments and some local variables are not present in the C code. This is an optimization that we do on the IM2 intermediate representation. So because in the in-place semantics, creating and reading, modifying and reading the memory creates aliases, it happens that B1 and BRES and CT1 are useless variables. They become dead variables, so we are able to remove them, and this is the result that we obtain after this optimization pass. So we directly mutate here the first variable CT and the length of the input buffer B. And also concerning the function signature, there is a one-to-one mapping between the Baroque signature and the C signature. So the input buffer is a pointer in C, and the return value is also a pointer, which corresponds to that on the Baroque code. And now I'm going to talk more details about S3K, which is a simple secure separation kernel. So it's a kernel developed at KTH. It targets RISC-V embedded systems, and it's based on capabilities. So originally, the implementation is in C and assembly. And the goal of this kernel is to guarantee some security properties which are related to spatial protection and temporal protection. So the goal of spatial protection is to isolate each processes from each other, and it enforces thanks to the PMP RISC-V mechanism. And the temporal protection relies on first the temporal reference to flush the cache at its context switch, and it allows to protect against side channels. And they also add time padding to avoid the execution time of processes to interfere with the execution time of other processes. And a little bit more about capabilities. So capabilities are tokens and enforceable tokens that grant access to a system resource. And one of the core logic of S3K is to manage dynamically those capabilities. So the main two operations are capability derivation. So a capability is going to delegate its rights to children capability. And the reverse operation, which is capability revocation. So the capability will reclaim the rights that it previously allocated to children. So the original implementation of Baroque was about 2,000 lines of C code and 200 lines of assembly. The number of lines for the Baroque implementation of S3K is roughly the same, so 2,000 lines of Baroque, but we have remaining C code in this implementation. And this C code is mainly used for interaction with the hardware and also some loops that could not be ported to Baroque for the moment. And thanks to this unboxing operator that changes the memory layout, we achieved the same layout for the kernel tables. To test that the kernel, the Baroque implementation of S3K was reasonably efficient, we run some benchmarks on real hardware, so on FPGA. And in this benchmark, we have two processes, a client and a server that are talking to each other. And we measured the time that the kernel take to handle the message sent by the client and the time that it took to handle the reply sent by the server. So in this setting, we have approximately 3% overhead introduced by the Baroque code for the runtime trip, which is the sum of those two times. We also rerun those benchmarks by adding a temporal fence just before sending the message for the client and the reply for the server. So basically, the temporal fence pushes the cache. And in these settings, the overhead is higher and is about 8% for the runtime chip. OK, so let's now conclude. So what we did in this work is that we have a new domain-specific language that is embedded in Rock and that we compiled to C. Something that I didn't talk in this presentation, but if you're interested, you can read the paper, is that we define a semantics for Baroque, and we prove that this semantics is sound with respect to how the Rock interpreters interpret the Baroque programs. We have a compiler that generates human-readable and reasonably efficient C code. And finally, we have an implementation of a state-of-the-art separation kernel. And for the future works, we would like to dig into some proofs, so proof of the compiler on S3K, and adding some more features to the language and finding more case studies for Baroque. Thank you for the attention. I will take some questions.
Thank you. Are there any questions?
Thank you. Andreas Koch, TU Darmstadt. I have a very minor question on this, but we are struggling with the same topic in my group currently. So I'm wondering, why did you compile using just -02 instead of 03?
It was an advice of one of the co-authors that say it's safer to compile with 02. So yeah.
But it's a performance difference. 03 will run faster, quite a lot faster in some cases.
Yeah, sure. But so I'm not the compiler C expert, and so we reused how the previous benchmark on S3K was done, and it was compiled with 02. Yeah, I think the main reason why it was not that an advantage to compile with 03, from what I understand. But yeah.
Okay, thank you.
Thanks. So your position is for microkernels, right?
Yeah.
But you have to also deal with assembly. So why is it not possible to translate your Baroque directly into assembly if you have a specification of assembly?
So what you will do is to define an abstract function in Baroque, so a function that does not have an implementation in Baroque, and that serves as the interface for the assembly implementation of those functions. And does that answer your question?
So let me.
Yeah.
The answer is that we already have a verified compiler from C to assembly.
Yeah.
Oh, okay, that was.
Okay, okay. So for everything can be written in Baroque, including the all the stuff relevant to assemblies, if I get it right. Yeah.
I mean, the thing that our assembly codes remain assembly codes.
Yeah.
It cannot be written in Baroque.
So if I want to write a context switch,
yeah,
for example,
yeah,
then I need to write some assembly, right?
Yeah.
That's what we do nowadays. But
So
can we also do some stuff in Baroque for context switch?
no, so for example, context switch typically will be written in assembly. Yeah.
I think my question was answered already. I wanted to ask about what is the subset that you compile to, and if that is the subset corresponding to ComCert. But I think you're using ComCert then.
Yes.
All right.
So the subset of work, right, or the subset of C, yeah. So we are targeting C syntax, the source language of ComCert, and I mean the subset is using the records, I mean structures, enumerations, ifs and else switch statements, and pointers, and yeah.
So I had one last quick question. Yeah. The style in which you have to write your functional code has to look pretty much very idiomatically like C. It's this continuation of let. Yeah. What if you wrote it differently? Would you get very bad behavior? Inefficient behavior.
So what you will have is just not a one-to-one mapping between the Baroque and the C code, but it does not affect the performances of the code.
Okay.
Yeah.
Great. Our next talk is on a pointer ownership model. Yeah, let's give a round of applause. Sorry. Yeah, thanks for so it's a pointer ownership model for C. It's inspired by Rust. David Swoboda and his colleagues at Carnegie Mellon Software Engineering Institute. David's going to give the talk.
Goes on the belt. Okay, so I think I'm mic'd up. Good. All right, so I'm here to talk to you about pointer ownership model for C inspired by Rust. So I'm going to start off with a little personal anecdote. When I was a student, I first learned about formal models, and I thought they're interesting academically, but they're tedious and expensive, and well, they take a lot of effort to do. So they're not going to escape out of the ivory tower. They're always going to be locked in academia. 5 years later, I learned about neural nets and came to the same conclusion. They're not going to escape out of academia. And well, in my defense, I was right for several decades. It's only been in the past 5-10 years that neural nets and large language models have become popular. And the fundamental question I have, which I don't have an answer to, but the notion is, can we use large language models to help us build formal methods and make formal methods more accessible and usable? So with that, I'll start the actual presentation. So, of course, C programs are not memory safe, and we're going to focus in this project on temporal memory safety. So we're ignoring things like buffer overflows. We're instead focusing on things like use after free and double free. So the argument is that we are providing a model of managing pointer ownerships, lifetimes. It's inspired by Rust, and it's inspired a little bit by C++'s Ray. And it's inspired by the discipline that every C programmer who's ever had a memory error in their program and spent hours debugging it, as I had, in my student days, they quickly have to develop something like this. So we have a model. It covers lifetimes, much like Rust. The model helps reduce the problem of proving temporal memory safety to a satisfiability problem. So it can be done statically without having to actually run your program. as you might guess, building a what we call a P model, that's the model applied to a specific program. Building a P model can be tedious and long because you have to represent every pointer, but LLMs can help reduce the tedium and make it cheaper. And finally, we actually have test results. We ran this on 4,000 cases from the Juliet test suite. So I'll start off with an example of code. For my students, I like to ask, what's wrong with this code and let them figure things out. For here, I'll simply point out what you can see pretty quickly, which is that the memory from error message is freed by line 15 by the usage function, and it's freed again by line 16, resulting in a double free. So this program is not temporally memory safe. So the problem is, in order to do that, you have to look at the code for both functions. We call that whole program analysis, and whole program analysis is it's workable in small examples like this, but it does not scale to real-world code that has more than 2 functions. So the idea is that we construct a P model for each function, which is what we've done here. And doing that, you can look at the P model and each function individually. So when you're analyzing main, you can ignore the code base for usage and just look at the P model and determine that error message becomes a zombie in line 15, meaning it points to freed memory, and it's freed again on line 16. So in other words, we don't have to run this program to see that it's not actually memory safe. So the main crux of the model hinges on responsible versus irresponsible pointers. For you Rust experts out there, they correspond to box pointers and references in Rust. And so we're basically trying to apply the same model that Rust's borrow checker has and apply to C. So responsible pointers are pointers that point to chunks of memory on the heap. And when the responsible pointer goes away, the heap memory should also be freed. In particular, each heap object should be referenced by exactly one responsible pointer. And therefore, that handles the aliasing problem. If we have a responsible pointer, we know that no other pointer can be dereferenced that points to it. So that way we safely manage heap safety. Irresponsible pointers are like reference pointers, are the blue ones in this diagram, and they can point to anything. They cannot participate in memory management, and the main concern with them is that they might point to something that eventually gets freed. So for example, if this chunk of memory gets freed, then we need to make sure that the pointer to it never gets dereferenced. That would be a use after free error. I'm not going to go over these other threes, well, except for diligent pointers, because diligent pointers are kind of the boring, read-only things that we'll see those a little bit in later on. And fortunately, most pointers are diligent. They don't participate in memory management. Okay, so this is what we wound up building, a combination of a builder and, well, this whole thing on the left is what we call a verifier. So the builder, of course, constructs P models, and in our case, it uses a large language model. In our case, we used GPT-04 Mini, but you could theoretically use any large language model today, or you can build P models by hand. The rest of this is what we call a verifier, and it either says, the constraints you have are satisfiable or they're not satisfiable. We're using a stat solver, and so if they're not satisfiable, you get an unsat core. And at the base of it, an unsat core is effectively a Boolean proposition. It's kind of a proof that things are not satisfiable in conjunctive normal form. So it will be something like A and B and C and not A, which is contradictory. So when we first built this, we kind of assumed that people would use the builder and the stat solver together, and the constraint generator that feeds constraints to the stat solver would pull constraints from the builder's P model, and it would infer some constraints from the LLVMIR, which is derived from the source code by Clang. We actually realized that there's a second subset here where you can dispense with the P model. That's why the P model line is dotted, and you just infer constraints from the constraint generator or from the LLVMIR. We call that the whole program stat solver because it simply answers the question, does there exist a P model that can satisfy this code or not? Is the code internally consistent or not? So that turned out to be useful for testing. It doesn't tell us what the P model actually is. It just tells us whether or not there exists one or none. So we wound up using that for testing. You'll see in the testing slides in a little bit. We expect that most people will want to use the builder and the LLM to construct P models. P models are actually good for representing the intentions of the programmer, and they're good to maintain as the program evolves. If a P model says this pointer must be good and pass to a function, and someone writes code that passes a null pointer to the function, that can be caught at compile time without actually, and save yourself some debugging effort. So ultimately, we have 3 tests that test the various components. The first test just tests the builder, and in particular the LLM. The second test tests the whole program stat solver and ignores the builder. And the third test puts things all together. So I'll go over each of these in turn. For the first test, we simply construct a manual P model and then ask the LLM to generate a P model for us, and did it get the answer right? For this test, we used the DOS Unix program. That's one of my favorite programs because it's fairly small. It has, 169 pointers. It's actually designed to solve a real-world problem, converting new lines between DOS format and Unix format, and vice versa. So I won't claim it's the smallest, but it's one of the smallest bits of open source code that actually does something productive. It was not just written for someone's homework assignment or someone to teach themselves programming. So we kind of hoped that the system that the builder would correctly determine the P models for all 169, or we were hoping for a 95% accuracy rate. We wound up getting 159 pointers correct, 10 pointers wrong, so that accuracy rate is just a little shy of 95. It's 94.1%, which is close enough. And what we have here is an error breakdown of the 10 pointers that were incorrect. We could easily put effort towards fixing one of these and to get ourselves to the 95%. But that 95% is an arbitrary limit that we set for ourselves. Okay, for the second test, we relied on Juliet. For those who don't know, Juliet is a large test suite released by NIST of about 50,000 small C and C++ programs. They're either good or bad programs. Bad programs violate a particular CVE, and each bad program says, at this line, we're going to violate this CVE. And the good programs are like that, but they don't violate the CVE. So, 50% good, 50% bad. And for our test, we are only concerned with the 5 temporal memory safety CVEs. So, again, we ran just the whole program stat solver, no LLM, no builder. Were these CVEs, or were these programs, were the good programs truly marked as memory safe, and the bad programs marked as memory unsafe? And as you can see in these pie charts, under both good and bad, there were 10% of programs that used features we did not support. There's some features that we haven't, well, note to self, don't ever say that we can't do this, just simply say it's future work. So, for instance, static pointers are future work. In fact, static mutable pointers are even not supported by safe Rust. So that's kind of something that we need to work on. So the 10% that is grayed out here were things that used features that are future work. Of the things that we support, all of the bad examples were recognized as bad by the whole program stat solver, and all but 9% of the good programs were recognized as good, and that 9% works out to 200 programs, and we did an error analysis of these 200 programs. So what we discovered is about half of these programs were cases that we said they are memory safe, but they violate POM. They violate our pointer ownership model, and in those cases, 100%, in those cases, I should add that one feature of our model is that it doesn't capture every temporally memory safe C program. It can certainly, there are certainly things you can do in C code that's not POM compliant, such as using reference counting or garbage collection or other more sophisticated memory management techniques. And what Juliet does in a bunch of cases is it takes a pointer that points to the stack, returns that pointer from the function. As you might guess, returning that pointer automatically makes it a zombie, and dereferencing that pointer would be undefined behavior. And in real-world code, you wouldn't return that pointer if you're not going to use it. But Juliet is not real-world code. It's not natural. It's test code, kind of artificial. And Juliet therefore has lots of code examples that return, zombie pointers, but never actually use them. So the code itself is memory safe, but it is not compliant with POM. A third of the examples were cases where the code was memory safe and I guess you could say it complies with POM from a programmer standpoint, but it basically used analysis techniques that foiled static analysis. For example, if you allocate memory using malloc, you're supposed to free it exactly once using free. Freeing it no times is a memory leak. Freeing it 2 or more times is a double free. Well, what if your free function is buried inside a loop, a for loop? Then the static analysis will say, sorry, this loop may execute 0 times or multiple times, not safe, not compliant with POM. Juliet, however, simply has a loop like what you see there, where the loop is designed to run exactly 1 time. So the code is memory safe, but our static analysis didn't recognize that the loop runs exactly once. And trust me, while this code may be memory safe, if you ever submit to me a merge request, a pull request with that kind of loop in it, well, I'm not going to be happy with your code. So on to the third test, where we put things together, the LLM builder and the SAT solver. And these were the results we get. The LLM produced the correct P models between 72 and 95% of the time. This only occurred, we only did 4,100 of the tests. Those are the ones that did not use unsupported features. So this is the results, and I like to think of this as a glass half full thing. Instead of generating 4,100 P models yourself, the LM got between 72 and 95% of them correct. When it gets things incorrect, then you'll get an unsat core for a particular function, and you would have to debug that function. So ultimately, if you wanted to get correct P models for all of Juliet, you would just have to fill in the tops of these things until they all reached up to 100%. That's a little bit of work for you, but the LLM has saved you from a lot of work. So speaking of work, future work. Again, lots of future work to do. We'd love to do this. This work in time, such as handling arrays of pointers, static pointers. There's a few functions, such as the real path function at POSIX, that simply are fancier than what our model can support. Likewise, we did all this work with GPT-04 Mini. There are newer, fancier models out there today that we can work with. To me, we have a sketch of a proof, but making that completely finishing the formal proof is future work. But to me, the most interesting future work is we've just used formal methods and an LLM to work on and partially solve temporal memory safety. Could we use this to do spatial memory safety? Can we identify buffer overflow statically? Could we do concurrency safety? Lots of interesting questions. So I'll give a quick shout out to my team who put this together. Some of them went beyond the call of duty. So they did a great job, great team. And so to conclude, we have a semi-formal model showing memory safety. We can use an LLM to build this model for any program. If the LLM hallucinates, then what we wind up getting is a positive, which might be a false positive. It might say this program that's temporally memory safe really isn't memory safe. It does not ever give you false negatives. It will never say this memory unsafe program really is memory safe. Hallucinations are caught by the SAT solver and produce unsat cores, saying the program is not memory safe. And as you see, the Juliet case correctly recognized all unsafe programs and recognized correctly most of the safe programs. So in conclusion, we have a website available and a GitHub project. The GitHub code was used in the artifact, the reproduction artifact. And finally, last thing is we will be giving a presentation of pointer ownership to the SCI Summer Series happening in Virginia on July, I think, 23rd. So I welcome you all to come over there and listen in on things. Thank you.
Applause. Are there any questions that people have for David? Oh, I should quickly mention that there are 3 of the badges given for this paper. For the previous paper, there was the red and the green badge, and the previous paper was a candidate for the best paper award for the conference. And the next talk, which is going to be given, is also got 2 badges. Well, just a question to David. How do you deal with, you had your irresponsible pointers, and if you did operations on them, change what they're pointing to or dereference them or something, how does your analysis catch that?
So the point of the analysis is to catch lifetimes of irresponsible pointers. So while you can perform arithmetic within an irresponsible pointer, it is important that it not exceed its array. That's a constraint in the C language. You can't like hop from this object to that object even if these objects happen to be consecutive in memory, unless they're part of like a single larger object. So the main thing is to simply make sure that the irresponsible pointer doesn't outlive whatever it points to.
Okay.
Does that help?
There's a question here.
Great talk. I have one question. So one of the parts of this is that LLMs do hallucinate. And you found in your code around 94% correctness out of curiosity. Does that change with larger code inputs versus smaller code inputs? Is it more likely to get like the smaller code inputs correct, or does it scale poorly or well?
That's a really good question, and giving a more nuanced answer to that question is future work.
Thank you.
So
Perfect.
DOS Unix is a fairly small bit of program. Juliet is a large test suite of small programs, so we haven't really gotten to answer that question on larger programs yet.
Thank you.
So just something that I don't think you mentioned in your talk, what's the timescale like on solving this model? How long does it actually take to analyze a model, run it through the SAT solver, et cetera?
Very good question. I don't have any of that data down because it always was instantaneous. So SAT solvers, of course, could take a long time if given really huge amounts of code, but we have not managed to give it a large enough code to make it take a long time yet. So future work again.
Thanks, David. Let's give him a round of applause.
Thank you.
Our next speaker is Norimatsu Tanaka-san from Tsukuba University. He's going to be talking about Hikami, a lightweight hypervisor for emulating RISC-V extension semantics with SAIL-driven auto-generation.
Okay. Yes. Yeah. Okay. Thank you very much for introduction. Okay. Okay. Thank you very much for introduction. I'm Naosa Takana. Came from University of Tsukuba, Japan. Today, I'm going to present to you Hikami, a lightweight hypervisor for emulating RISC-V extension semantics with SAIL-driven auto-generation. First, I'll provide a brief introduction to RISC-V. RISC-V is a modern open-source instruction set architecture. Its royalty-free nature encourages innovation and allows for significant customization. A key aspect of RISC-V is its modularity. ISA is divided into extensions allowing hardware designers to include only necessary features. However, this modularity has led to a significant challenge. As shown in the diagram, the number of officially RISC-V extensions is growing extremely rapidly, with nearly 150 standard extensions currently defined. In contrast, the number of extensions actually available in silicon lags far behind. According to our empirical survey, only about 40 extensions have confirmed adoption.
There's a red dot there. It's from your purple. Yeah, that's good.
Yeah. Okay. Oh, sorry. Only about 40 extensions have confirmed adoption in commercial community hardware. This creates a severe adoption gap. This hardware gap is our first problem. Extensions range from simple instructions to complex features with nuisance styles and exceptions. It is impractical to build hardware for every combination, leaving developers without target hardware for early software validation. The second problem is ecosystem stagnation, a chicken and egg cycle between the hardware and software development. While emulators like QM exist, they abstract low-level interaction, making a hardware-coupled validation difficult. So how can we bridge this adoption gap? How can we enable early software validation without waiting for expensive silicon? To bridge this gap, we need a validation environment on physical hardware maintaining a native speed for existing code. The key requirements are ease of use, high reliability, and near-native performance. Next, I will review existing approaches for extending the ISA and their limitations. One approach is hardware-assisted validation using FPGAs. The ROCC interface allows extending the processor with accelerators that are tightly coupled via the on-chip bus. This setup receives the instruction as commands and returns results, enabling hardware-level ISA expansion with a low latency. While high performance, it requires costly FPGA synthesis for every configuration, limiting early-stage software development. Another approach is a firmware-level emulation via projects like OpenSpace H using illegal instruction traps in M mode. While portable, executing emulation in M mode, which is a highest level mode, violates the principle of least privilege and incurs high overhead due to lack of virtualization support. To address these challenges I mentioned earlier, we need to choose the right privilege level for emulation. Existing M-mode firmware has a high overhead and security risks. U-mode emulation is secure but slow. Our research focuses on a Type-1 hypervisor in HS mode, leveraging virtualization for a low overhead while keeping emulation logic isolated. Based on this approach, we developed Hikami. Hikami is a lightweight Type-1 hypervisor specifically designed for RISC-V. Our primary design goal was to keep the trusted computing base as small as possible, focusing only on essential functions like memory management and trap handling. This architecture allows the guest OS to run at near-native speed and provide direct access to hardware peripherals, meaning we can use unmodified and vendor drivers. Yeah. Emulation logic is implemented as a modular hypervisor modules, corresponding one-to-one with RISC-V extensions and are integrated using the Rust Create system. For example, supporting the ZBS extension requires only adding 2 lines to the configuration file. It drastically reducing a setup cost. Supporting extension requires handling 3 core elements. Trapping new instructions, intercepting new CSR or control and status register accesses, and injecting new exception causes. For instruction emulation, when the guest executes implemented instructions, it triggers an illegal instruction trap to the hypervisor. The hypervisor then decodes the instruction and execute its semantics in software by updating the guest register's context, and finally returns the control the guest as the next instruction. For CSR emulation, the hypervisor intercepts access to the new CSR and diverts them to a virtual CSR state in a protected memory area. For exception injection, we simulate the new exceptions by directly modifying the guest system register, forcing the guest to jump to its exception handler. While this architecture is powerful, implementing these modules manually remains a challenge. Developers must exhaustively list all new instructions and manually write complex bit masking logic for decoders and implement a lot of boilerplate code. This manual process is not only labor intensive, but also highly prone to subtle bugs. So how can we automate this process and ensure its correctness? To solve the challenge of manual implementation, we propose an automated framework driven by formal specifications. As I mentioned, manual implementation is labor-intensive and error-prone. Developers have to manually parse the PDF specifications and transcribe bit patterns into code, which is a major source of bugs and inconsistencies. Our solution is to automatically generate instruction decoders and hypervise the module templates directly from the sales specification. This ensures that our emulation logic is always in sync with the formal ISA definition. So what is SAIL? SAIL is a formal language specifically designed for describing the semantics of instruction sets. It is already widely used by the RISC-V community to generate official documentation and test suites. By using SAIL, we leverage an authoritative and unambiguous source of truth for all RISC-V extensions. This is what SAIL code looks like. It defines a mapping between the instructions and the binary encodings. Our framework parses this definition to extract the necessary information for automatic generation. First, we generate the hypervisor module templates. The hypervisor module are the core of our emulation system, so it is critical to avoid the implementation gap or logic errors. To achieve this, our framework automatically extracts the extension name or defines instructions and all new CSRs directly from the SAIL source. This ensures that no part of the extension are overlooked during the implementations. The framework produces a Rust template with a much expression for every instruction. The developer only needs to fill in the semantics logic for each case by replacing a to-do macro, like this. This drastically reduces the boilerplate code and prevents the human implementer from overlooking any specific instructions. And the second part of our framework is automatic generation of instruction decoders. To handle traps, the hypervisor must convert low binary sequences from guest memory into structured instruction object. Writing these decoders manually is extremely tedious and error-prone due to the complex bit field mapping in RISC-V. We automated this by analyzing the ENCDEC maps in SAIL. By identifying the construct opcodes and variable operand bits, a framework can automatically derive the logic needed to identify and disassemble any instruction. Our generation workflow follows 5 steps from extracting instruction to constructing a deterministic decision tree. The final output is a set of optimized Rust match expressions that provide fast and correct encodings. Our framework builds a hierarchical decision tree from field data. This ensures that every possible bit pattern is mapped to either a specific instruction or an error, providing us systematic coverage of the encoding space without manual errors. The emitted Rust code is clean, efficient, and guaranteed to match the cell specification. By automating this, we eliminate a major class of bugs commonly found in manually written emulators. And finally, we generated automated unit tests to verify the decoders. And the framework synthesizes instructions with random operands, encoding them according to the specification, and then check if the generated decoder can correctly pass them back. This provides an additional layer of assurance for our implementation. Now, let's look at the evaluation. We evaluated Hikami from 2 perspectives: emulation performance on physical hardware and overall impact on the system, including resource efficiency and real-time responsiveness. Experiments were conducted on the Milk5 Megres, a real RISC-V platform supporting the hypervisor extension. For fundamental validation, we targeted the ZBS bit manipulation extension, which is not natively supported by the hardware. We verified that the guest program using these instructions could run correctly on the physical board. This successfully demonstrated that Hikami can provide the correct semantics for unimplemented extensions on real silicon. To measure the emulation overhead, we conducted the number of instructions executed by the hypervisor to handle the single B-set instruction trap. Emulation overhead is approximately 300 instructions per trap. About half comes from the modular dispatch mechanism, a trade-off for ease of use. Hikami is lightweight with a core of about 7,000 lines of code. More importantly, our auto-generation framework provides a huge product regain. In the database module, nearly 75% of the code was generated automatically. The developer only had to write 28 lines of isolated semantics logic, which is significantly reduced the potential for human error. Finally, we compared Hikami with QM. Using CoreMark to measure environment file performance, Hikami maintains 99.8% of native performance. In contrast, QM's full emulation operates at only 8.5% of native speed. And in realistic workloads, such as OS boot or driver initialization, implemented instructions typically account for less than 0.1% of total execution. In these scenarios, Hikami is up to 3.4 times faster than QM. This makes the Hikami a superior validation environment for complex hardware-coupled software stacks. And to conclude, we propose a system combining virtualization and automation to address the RISC-V hardware gap. First, our lightweight type of hypervisor enables a near-native execution with a modular support for new extensions. Second, our cell-driven framework automatically generates a decoder and templates, eliminating manual errors and reducing implementation effort. Third, and finally, evaluation of real hardware shows our system maintains a 99.8% native performance, achieves a sub-microsecond latency, and outperforms QM in realistic workloads. This lightweight design provides an efficient foundation for testing and retrofitting new extensions. So thank you very much for your attention.
Thank you, Norimasa-san. There's lots of time for questions. So do we have any questions? So while other people are thinking of their questions, just wanted to ask you first, a lighthearted question, which is, what does hikami actually mean in Japanese? Does it mean something? Huh? Does the word mean something?
It is a distriction name.
Okay. Oh. Yeah. All right. So one of the things I was interested in knowing is, you trap an unsupported instruction, and then you're going to go to the hypervisor. What happens to the instruction decoding pipeline? Do you just do you start the execution of the decoding of the next instruction, or do you pause that? So suppose there's you take something from the extension, you're not going to execute it in native mode, but the next instruction in the pipeline, do you start decoding and start processing it at all if that's in native code? If that's in native mode?
We decode each instruction one by one. Okay.
Yeah. So you're not considering the possibility of you're going to interrupt the pipeline and okay. Yeah. Are there any security implications of running things in HS mode versus native mode? Could you comment on that?
I can solve this aspect.
So there could be some security implications, right? If you're emulating something in hypervisor, yeah, versus how it would have run on if it was really supported on a machine. How do you deal with those information security leakages and so on?
RISC-V H extension, hypervisor extension supports memory isolation.
You have memory isolation?
Yes.
Okay, all right. And you prefer the HS mode over the M mode?
Sorry?
Is the HS mode always preferred over the M mode for security reasons?
Yes.
Okay, all right. Any other questions? Sorry, I've been asking the questions. Yeah. Okay, let's give Norimasa-san a big hand.
Thanks so much.
Thank you very much, and remember to check out the artifacts, right? Play around with them. The last talk, and let me get this in my hand. In this session is a work-in-progress talk. It's scheduled partial credit RL for reliable code generation with small language models, and Suryansh Singh Sijwali is going to present it. You're from Penn State, is that? So, thank you. So, the mic is here. Thank you. Okay, so it's 10 minutes. What I'll do is I'll give you a finger saying 2 minutes or so to go. All right? Yeah.
Do you have an HDMI connector? I think so, yeah. Let me try. Oh, no, it works. Yeah, I thought I was missing a part. Hello everyone. So to present this, all right. So I'll be presenting this checkpoint of our overall work that focuses on improving code generation processes in small language model. So here we are focusing specifically on scheduled partial credit RL pipeline. And I have configured the presentation into answering 4 specific questions, which are why, what, how, and what's next. So answering why first. So why are we focusing on small language models specifically? We all know that LLMs are like pretty good at code generation. They're beating benchmarks every second month. So why are we specifically focusing on small language models? So the very direct answer would be that small language models can really fit inside of our specific deployment, inside of PCs, inside of edge devices. And if you go very small, you can also fit them inside of some embedded systems. And what is the problem that we are really solving? Because there are small language models that are fine-tuned for code generation. Now, the thing we found out was that these fine-tuned models usually produce only 50% of syntax valid code, which is a really big issue because these models promise really good security or secure code, but only 50% of them are actually syntax valid. So there is a big loophole in there. What does our work specifically entail? We also set out to solve the security paradigm, but the issue is not really security. The issue is compilation, because a lot of these models actually promise more than 80% of security valid code, security clean code. But if you go in deeper and analyze the secure code, you find out that 50% of them are stubs that don't really even compile. But since they don't have a vulnerability that can be caught by an SAST tool, it comes out as secure clean, but the code actually does not even compile. So we found out that reliability is something that we have to focus on. We have to focus on code that actually compiles first, and then we can focus on security. So we pivoted to producing code that actually compiles and is syntax valid first. And for that, we created a joint reward, which basically prioritizes code functionality over code security. So how does this solve the problem? We started off by selecting a baseline, which is very low in terms of the number of parameters, which is 1.3 billion. This is a pre-fine-tuned version, so DeepSeek Coder is fine-tuned for coding. But even so, the baseline only produces about 20% syntax valid code. So we applied a LoRa-based supervised fine-tuning pipeline, and we use apps plus dataset as the baseline for the fine-tuning. This only fine-tuned about 0.43% of the total number of parameters. So total number is 1.3 billion. We fine-tuned close to like 60 million. And this was only behavioral fine-tuning, and we did not really do anything with how the model produces code. And we saw significant improvement there, but the main RL portion comes next. So after we got the supervised fine-tune model, we ran it through a PPO training pipeline, which consisted of a double reward setup, which included a functionality reward and a security reward. The security reward consisted of the banded SSD tool. The functionality reward basically consisted of how many test cases it's passing. And from that, we got our main model that we'll be evaluating later. And how did this solve the problem? So the main problem we face when evaluating or when training small language models is that the reward is too sparse. So the model finds it really difficult to learn anything based on the binary rewards. So we broke down the reward into partial credits. So it can sort of have a ladder to climb. We set up like specific milestones for the functionality reward so it can be easier to train it. If it's syntax valid, that's like the minimal requirement, it will get at least some reward. And then if it's passing more and more test cases, it's getting the full reward. And to maintain the security part of our reward, we had a guardrail using medium and hard security vulnerabilities. If there are any, it will basically not give any positive reward to the model, and the reward will degrade. So the model is forced to maintain security while also focusing on reliability. And the result we got was pretty significant. So as I did mention, that binary reward is really sparse when we go down the scale in terms of small language model training. So the binary reward actually is worse than what we got for our SFT model. We only got 18% syntax valid, which is like 26 percentage points less than even the baseline. This happens because just using a 0 or 1 for functionality does not really teach the model anything at this scale. Because just think about it this way, if you don't know about a specific topic and you're attempting it, you won't be able to learn without any feedback what you're doing wrong, right? So it's difficult for the model to explore and gain any insight about what's wrong and what's right. With the partial credit, it improves slightly, but what really helps is a schedule framework. So we give our model a warm start using the binary framework, and then move on to partial credit. So it has a very rigorous exploration set up by the binary because it's not able to learn anything, so it has to explore by its own. And with the partial credit, it's sort of smoothened. And because of that, we get a really high syntax validity score in our curriculum model. Now, this is just what we have done so far. Since this is work in progress, there's a lot we can do in the future as well. The very first thing would be to tighten the reliability result. That's because our current version does not really have a very tightly bounded CI. So we can probably run more seeds, run more steps to get it to like plus minus 2%, I guess. And secondly, we can also fix the hyperparameters and ensure that we are using the best ones. We can run a rank-based ablation for our fine-tuning platform. We can also play around with the learning rates. There's a lot of other ablations we can do. We can generalize the small language models and try it on different RL algorithms. For this, we use PPO, which is just one of the many. PPO is not really memory efficient as well, so we can probably try GRPO. There's a lot we can do. But our primary end goal is to create a model that's both reliable and secure and generates good code in the end. So the key takeaway of this presentation is that sparsity is the failure mode in terms of binary credit in both security and functionality frameworks. And to fix this in small language models, we have to utilize some sort of curriculum or scheduling to get around the failure mode. Thank you. I'll take in any questions now.
Thanks, that was very timely. And okay, any questions? Great.
Hi, thanks for the talk. Sorry if I missed it at the beginning, but what language are you asking these LLMs to generate?
So for this, we focus on Python. And we have extended this to 3 languages, C++ and C as well.
And do the results vary by language in terms of syntax validity %?
So syntax validity does not really matter as much in terms of how or what language you're using. But for security, it's mostly that Python is very highly compile, and security is like, if we take both of them into account, Python is the most reliable, and C and C++, the LLM really, or the SLM really struggles with it for some reason. So yeah.
By reliability, you mean, or as in you mean the C and C++ programs are less secure than the Python ones?
Right, yeah.
Probably just because C and C++ are not memory safe?
I believe so, yes. So we tried 19 CWEs when we were testing for the security relevant prompts, and 8 of them were memory focused, and those were the most erroneous ones too. So yes.
I guess that makes sense then. Thanks.
So do we have any other questions?
Yeah, just a short question. Thank you for the talk. So, because in the first slide you show the small model is DeepSeek, right? So I'm just curious about what's the reason to choose this model. Is there what's the problem for the other small models? Yeah.
The DeepSeek 1.3 billion.
Oh yes.
Is it this one?
Yeah. So yeah, this one you said you are using DeepSeek model, and I'm just curious why you choose DeepSeek at this point. Is there any problem with the other small models? Yeah.
All right. So 1.3 billion parameters is like one of the lowest ones we can have that is fine-tuned for coding. That's one of the reasons. It's open source. That's another reason. So we started off with 7 billion parameter models, but this actually beats them with the whole pipeline. So it's sort of like setting up the lowest point we can train the model from and get our results high. Yeah.
I see. Sounds good. Thank you.
Yeah.
Any other questions? If not, let's give Suryansh a big hand. And I'd like to thank all of you for participating in this session. I want to thank the speakers. Let's give them all another round of applause. I think we had a great thing. And remember, the first talk was a candidate for Best Paper in the Conference Award. And there were 2 candidates, and this was one of them. And as organizer, do you want to say anything? So then we meet after lunch. So enjoy yourselves. Thank you again.
Lunch today was really good, so I don't blame you if you fall asleep during my talk, especially since I'm used to it. When I'm teaching classes, all my students are sleeping too, so it's okay. Oh, there you go.
Let's get started. Welcome to session 4, Specialized Hardware and Accelerator Design, LCTES. And hope you guys enjoyed our lunch. As Scott, our first speaker, Scott, mentioned. Scott is going to introduce his research paper, Can Fine-Grained Multithreading Subsume VLIW?
Right, thank you, I appreciate it. So yes, I'm Scott Pomerville. This was a paper in conjunction with Michigan Tech and Florida State as well. I'm from Northern. This is an homage to, the title is an homage to Can Data Flow Subsume von Neumann Computing? So if you know the history of that, the answer ended up, of course, now you know, is no. So don't assume I'm promising the moon because the answer might be no. But we're going to try our best to convince you that there might be a case here. So really quick, we'll just jump through here and just give a background because VLIW, it's a thing we don't really think about every single day. But this is kind of what a VLIW looks like if you squint really hard. So over here, you can see an instruction stream. And this is a 3-wide VLIW. Oftentimes, VLIWs are powers of 2, but this one, I'm just trying to illustrate it. And each, essentially, instruction is a bundle of operations. So you have an add, a subtract, and a load word as part of an instruction. Then the next instruction might be a store, a multiply, and a no-op. And each instruction is going to end up essentially getting fetched by this fetch unit, and then the first third might go into this sort of pseudo pipeline here. The second one goes into kind of this pipeline here, and the third instruction would go into this pipeline here, or vice versa. So, or something like that. So the idea basically, though, is that a VLIW processor is much simpler than what we consider our modern superscalar processors, and these instructions are going to have to be essentially set up in a way, or these operations are going to have to be scheduled by our compiler. To maintain alignment, we oftentimes pad these instructions out with no-ops, although we try to then compress them afterwards with specialized hardware. But that's the basic idea and very simple version of a VLIW. And we're really only going to be talking about the basic versions here today. So the motivation here is really, with VLIWs, parallelism is bundled with sort of this instruction representation. VLIWs have these no-ops, and compiled code really needs to match VLIW width. So if I have a 4-wide or 8-wide VLIW, I need to make sure my code matches that width exactly, or have, again, special hardware that's going to modify, for instance, the PCs, or the PC increment, to handle different width code, which means we have to have specialized hardware for backwards compatibility. But what if we have a different encoding? What if we consider that this might not be the only way to represent parallelism statically? New representation might have some potential to handle some of these problems natively, and also, while we're at it, might give us some new avenues for research. So instead, well, what's another way we oftentimes do it? Oftentimes we use multi-threading, and that's really nice, but requires some extra intervention. So instead, though, what if we just take these VLIW packs and treat them as lockstep threads instead? So here I have some instructions here, and I've just sort of removed the actual instructions and replaced them with I1, I2, I3. And so you can see here, or operations. What if instead we just have multiple PCs? Each one is going to run sort of in parallel in lockstep. You notice each lane has its own PC. And then what happens if we then apply maybe some simple synchronization mechanisms, just the ability for lanes to just turn off and on again when they're just told to. In that scenario, what we find is that we can basically eliminate most of the no-ops, if not all of them. At least, that's kind of the hope. And so what we're going to do is essentially treat these sort of individual sort of pseudo-threads as a different stream, but each one is going to represent sort of the different parallelism, or the parallelism that a VLIW would by using long instructions instead of using these synchronized threads. So what we're going to do is really add just a quick piece of terminology here, this idea of a lane. And a lane is really just sort of this pseudo thread coupled with the corresponding hardware that it's going to run. Because if we remember that VLIW has one single fetch unit and then a bunch of essentially just simple pipelined processors that share a register file. The idea is instead, let's just make sure that each sort of pseudo thread has its own individual fetch unit and go from there. We're going to define lanes essentially as being in one of three states. An active lane is just going to fetch instructions from whatever its corresponding stream of instructions are and run them like we expect. There's suspended lanes, and a suspended lane is one where what we'll do is we'll just say, hey, if you're running and you suspend, don't fetch or do any instructions there. And so that'll allow us to essentially not have to encode those instructions. And then in a halted or inactive lane, it's just a lane we never turned on. It doesn't actually have a corresponding instruction stream. It's just the hardware that's shut off. To prevent deadlocks in this sort of pseudo multi-threaded situation, we'll have lane 0 be always active, and every other lane we'll refer to as like 1+, essentially. And those ones can turn off. And this entire architecture, the corresponding hardware, as well as sort of this instruction representation, is going to be referred to as a synchronized lane architecture, because I'm not really good at naming things, all right? So the most significant bit is actually going to be one of the most important parts, and we're going to talk about that a little bit in a moment. The ISA that we provided is actually a from-scratch ISA. It looks a lot like MIPS, because I might as well use something that mostly exists so that I don't have to do everything from scratch. But it is its own ISA, we call the SLA ISA. And it has a bunch of instructions, all dedicated to spinning up instruction streams, as well as halting instruction streams as we go, entering functions, and so on and so forth, because a couple things are going to change. We won't be able to get into that, but if you're curious, you can read about it in the paper. We have several registers as well that are also just really there to administratively be like, are you running or are you not running, right? For states, as well as if we enter a function, normally we have to keep track of one PC. Now we have to keep track of a handful of PCs. So we have extra registers for that. The main kind of important part, though, is this idea of being able to turn on and off lanes, which is really just a single bit in the instruction set that we call the suspend resume bit, or an SR bit. A suspend resume bit sits as the most significant bit of any instruction, and that way we don't have to decode the instruction to know if that bit is set. We can simply use it, and the idea here is I'll just add a .sr in my assembly to say, hey, this bit is set or not set. So all instructions basically have two versions, one where it's not set and one where it is set. So an addu would become addu.sr. And that just says, when you fetch this instruction, don't fetch any more instructions. You're done, and you'll suspend. At least that's true for lanes 1 and so on. So if they see that, that's just the last instruction you're going to run. It'll run through the pipeline and do what it does normally, but it will no longer fetch instructions, and it suppresses any access to the instruction caches, and each lane has its own individual instruction cache. Lane 0 has a .sr extension, but since it can't turn off, all it says is all other lanes that are currently suspended but still have a PC, resume execution. Halted and inactive lanes do not have a PC, so they won't continue. So that's the basic idea of these SR bits. For branches and jumps, because each lane has its own kind of thing going on, we need to make sure that when a branch is taken, all of the lanes update their PCs, but it would be terrible to duplicate all of those branches and have a whole branch taken buffer for each lane. So instead, we offer just a single register called a prepare branch register that just stores a PC. And whenever a lane encounters a special instruction called a PB instruction, it just puts a value in that register. And whenever lane 0 takes a jump, all other lanes that are suspended update their PC to whatever that PC is in the prepare branch register. So that's the basic kind of concept there. When entering a function, all lanes kind of halt, just to make sure that the processor is in a predictable state. They all lose their things except for lane 0, and lane 0 begins execution right away. So the basic idea is then lane 0 will be in charge of starting up new instruction streams to regain that parallelism that we want. One advantage of this scheme is that since entering a function halts all lanes, the processor, if you have some, let's say, a 4-wide processor, and you hand it 2-wide code, or a code that's designed for a 2-lane processor, those 2 lanes that are never used simply never spin up, and so the code actually natively is supported by code for smaller processors is natively supported by ones for larger processors. We just don't utilize the full hardware. So what ends up happening is we end up with a processor that looks like this. It should look very similar to the VLIW processor from before. The only difference is we've broken up the instruction fetch stages so that each individual lane has its own instruction fetch and its own instruction cache. So each cache is smaller, but this allows us to essentially allow certain lanes to shut off when they are not fetching and processing instructions. So this is a big idea. One thing you can see is after, for instance, the list load word, we added the .sr mnemonic to turn off this lane, and you can see there is no instructions that are fetched during that time. The load word .sr and this load word would be next to each other in the code because there's no need to have no ops there. So that allows us to actually compress the code while we're at it. And you can see that the lanes resume execution when we encounter a load word .sr in lane 0, which just spins up the other lanes again. So that's the entire premise of this architecture. The front end, these look really scary, but they're just standard pipeline processor front ends. The only difference is in lane 0, whenever there's a branch that's taken, it'll send a message to the lanes that are not lane 0 saying, hey, resume execution. So that's what's going on there. Or sorry, update your value to your PB register. Sorry, the resume execution is the other change, which is right here. Whenever we enter the instruction cache, we peel off the most significant bit and just say, hey, if it's 1, tell everybody to suspend or to resume execution if you're suspended. Over here on the hardware for the other lanes, it looks very similar. There's a couple small changes. The first change is that I don't have to have a full BTB. I just have a register with a PC in it. That's a PB register. And I have a 2-bit register called the lane status register that suppresses PC updates and instruction cache accesses whenever the lane is either suspended or halted. So that's the main difference there. And you can see I peel off that SR bit to suspend if I ever fetch an instruction from my instruction cache that has an SR bit. Those are the main differences. There's a couple other small wires there. They are described in the paper. So one thing we had to do when we made this and we did all this really cool stuff was figure out how to compare apples to oranges. VLIWs and VLIW processors as well as the SLA processor, they actually, because we use a bespoke ISA, all of the ISA is actually the same between the two processors, but they still execute a different number of operations. VLIWs have extra no-ops to maintain alignment, as well as SLA processors have some administrative functions or instructions. So those administrative instructions, unfortunately, we don't execute those in the VLIW. So we have these apples to oranges comparisons. So instead what we've done is essentially pinpoint the instructions that are unique, namely the no-ops and these administrative instructions, and we just omit them from the results. Because what we find is all of the other instructions are identical, right? So what ends up happening is in the same number, if you execute n functions, they will execute the same number of operations and the same kinds of operations, aside from the differences in these no-ops and these sort of what we call meta instructions. So whenever we are looking at statistics, what we're going to do is only count non-meta instructions for performance, because the meta instructions, which are these no-ops and these these administrative functions, don't really contribute to the core semantics of the program. They're just there for correctness. So these meaningful instructions are part of the core control flow. They are shared between both processors, and in any window they execute of functions or branches, they execute the same amount. We verified that. I won't jump too much into that for time reasons, but they're there so you know I didn't make up a fake processor. So we use Spec06 benchmarks. If you're wondering why we use such old benchmarks, it's because it was very hard getting this thing running in the first place and making a new ISA and a new compiler and everything else. We warmed it up for 2 billion non-meta instructions and then ran for 10 billion non-meta instructions, these meaningful instructions. And we tried 2 SLA processors, one where we give the lane 0, which is always on, a larger instruction cache, and one where we kind of just equally distributed the instruction cache for the processor. we've evenly distributed it with the 888, and then lane 0 gets extra space with the 16844. We use an in-house assembly optimizer called ASOpt, as well as FastADL for our cycle accurate simulator, and Cacti 7 for power calculations. And we looked at both 4-wide and 8-wide configurations, but we'll only focus on the one. So meaningful IPC, short version, they're about the same. So that's really what it comes down to. We do it slightly better than VLIW, and that comes from the fact that while we have extra loads and stores from lane state management, our instruction cache misses are slightly lower per lane. Now, if you were to sum these numbers up, they'll actually be very close to that number, but one advantage is after a jump, multiple lanes can miss at the same time, so we can interleave requests to level 2 cache, reducing effective miss penalty. So what ends up happening is that we end up actually having very similar performance. The instruction fetch energy is actually reduced, and this is primarily the instruction cache, and we find because lanes shut off, if a lane shuts off or is suspended, we suppress the request to the instruction cache. Those instruction caches don't run. If all lanes are active, the SLA processor uses slightly more power, but as soon as a lane suspends at all, we start to gain significant power, significant performance when it comes to power. Total instructions encoded as well, because we don't have to encode no ops. What we find is that the SLA processor, again, significantly reduces code size. We have tried 4 and 8-wide. So the 8-wide VLIW, of course, is significantly larger. The SLA processors, however, use less instructions to encode the same amount of information, since they don't have to encode no ops. So kind of in conclusion, just so that I don't know how much time I have, but I'm trying to make sure I'm quick because I went over time. But short version, we made this proof of concept processor. It was meant to be not necessarily a full working processor. The VLIW and the SLA processor were pretty bare bones. But it's a nice proof of concept to show this new code generation and corresponding hardware is something that's actually practical and doable. We showed the SLA, at least out of the box, has similar performance to a VLIW processor, while really providing these significant reductions in fetch energy and code size. And we also delve a little bit into the scalability in the paper. Just can't do it really quick here. And really, there's 2 major things we want to work on in the future. The first is meta instructions do have a non-negligible amount of overhead, especially in function calls, because you have to keep track of more things. We want to aim to reduce that overhead as we move forward in designing sort of this SLA processor. The second thing is we actually want to target more state-of-the-art systems using sort of this, in quotes, multi-threaded architecture, because what we would like to do is really improve and work on this sort of idea of having these sort of parallel pseudo threads. So I want to thank you all. I appreciate it. And do you have any questions? All right, I got 1 million. Great.
Yeah, thanks. Maybe a very quick one.
Yes.
So you said that lane 0 would activate all of them at the same time, but that may not, I mean, you may have some...
Right, you might have some propagation delay, for instance, right?
No, but what I'm saying is that maybe in the schedule, you just want to activate lane 3.
Yes, so this is actually where sometimes we have to deal with a no-op. We just have a no-op.sr to put one lane that activates for 1 cycle back to sleep. Yeah, it's one of the only times where we kind of still have to use no-ops.
And very quick clarification for the evaluation. So you said that you only measured like the effective payload instructions?
Yes.
Would that, like the results that you showed, would they also, if I now measure the end-to-end, say the latency of executing the entire thing, will the results be the same? Or will these extra meta instructions?
Yeah, the meta instructions, yeah, we based it off, yes, they will map 1-to-1. So if you have in any window of time, the meaningful instructions are the instructions that are consistent for the both processors. And we ended up, I did a lot of work in actually testing that out to make sure that that measurement was correct. Yes.
Okay, yeah, I'll trust you.
If you're curious, I can talk about it offline too. Yep.
Cool. Yeah, very interesting idea. I guess the first thing that came to my mind is like VLIW with stop bits, right? Something like Itanium, where you can compress no-ops. And I'd be curious. So specifically talking about iCache fetch, is that one thing about having a contiguous instruction stream of bundles is that your memory width response is going to be like 512 bits or something. And if you have a bunch of contiguous bundles, you're going to have a lot easier time filling that compared to if you have to find, if you have 4 lanes, you need to find 4 512-bit, unless you're doing like fetch fusion without control flow divergence. Does this make sense? Where it might be easier to have better iCache behavior if you have contiguous instruction stream rather than 4 independent ones?
Yeah, so I completely understand where you're kind of getting at it, is they're all over the place. So one thing that's kind of useful is because the instruction streams they're contiguous in the lanes that they are in. So lane zeros, all of their operations are still contiguous in memory. So what we found is, at least within the simulations that we were testing it out, that there is what we end up doing when we lay it out in memory is having lane zeros code followed by lane one's code followed by lane. So oftentimes, especially in smaller functions, you end up getting a lot of the same performance. It ends up not being a significant impact, especially because lane 0 is always running, and it ends up getting those benefits so that when you fetch something, it takes longer for one of those lanes to actually end up missing if you are not having a branching control flow. That was at least kind of the, I think I might have answered the question.
So if I could just follow up a tiny bit. I think that makes sense. My question would be for when you do have a lot of control flow, and you're trying to at least be able to access everything in your lane before you branch off somewhere else. Having a contiguous instruction stream across all the lanes allows you to fill that better, right?
Yeah, that's a good point. That might take a little bit. If you would like, I'd love to chat with you after.
Sure.
That might be that's a longer kind of answer.
Yeah. But very interesting thought.
Yeah,
I think this is a cool idea.
Yeah.
We can take more question.
Yes.
Right. One more.
Yes.
Very briefly, I'm not entirely clear how you're handling control flow. So you're saying only lane 0 can handle the control flow.
So,
no problem. In VLIW, often only op0 can handle control flow. But in a VLIW, I only have 1 program counter to set. Here I have 4 or 8 to set. How does it work?
Okay, so short version, I'll come back really quick to let's go to the hardware and corresponding software. So short version is lane 0 is the only lane that has access to the BTB. All right? So lane 0 here, if I access the BTB, and let's say I assume or I predict a taken branch. We're going to broadcast that information to each lane. And lanes, say this is lane 1. All that's going to happen is there's going to be an incoming signal from lane 0 here. All right? And what might happen is if I predict taken in lane 0, all other lanes have an instruction called a prepare branch instruction that before any branch is taken, they'll all get one. And if a branch is taken, that says, okay, now copy the PB register into the PC and just start executing there. Naively, you don't need to know why, you just need to be told to do it. Okay, got it. Does that help a little bit?
Yes, of course it does. Thank you.
Glad to hear.
Let's thank our speaker once again.
Thank you.
All right, our next speaker is Luis from McGill University. He's going to talk about his research papers, Syrup, a small IR for HLS with parallel patterns. Whenever you're ready.
Is it okay here? Hopefully it'll be okay. All right, good afternoon, everyone. Thanks for the introduction. Yeah, I'll be presenting my work on designing a small intermediate representation for high-level synthesis with functional parallel patterns. All right, so since I'll be describing a new language, I guess I'd better start by clarifying what sorts of programs am I looking to express with this language. Specifically, I'm looking to describe streaming accelerators that run on an FPGA. Now, FPGAs are interesting because they're a nice middle ground between application-specific integrated circuits and general-purpose processors like CPUs and GPUs. On one hand, you have the flexibility to really customize your hardware for your specific app, which helps with power efficiency and performance and so on. But on the other hand, you don't incur the cost of manufacturing your own custom chip. You just reprogram the device. Now, let's say that somewhere on this FPGA, you have a component that performs a dot product. And for illustration, I'll just use these simple inputs 1, 2, 3, 4, and 5, 6, 7, 8. Now, in a streaming accelerator, these inputs are provided piece by piece rather than all at once. So for example, maybe at the first clock cycle, we provide the inputs 1 and 5. And then at the next clock cycle, 2 and 6, and then 3, 7, and then 4, 8. And then later, we should get the answer, which is 70 in this case. So what options do we have for designing these sorts of streaming accelerators? Well, traditionally, you would use a hardware description language like VHDL or Verilog, which gives you a lot of control over the result, but it's very low level and verbose, right? It's kind of like writing your software in assembly. Like maybe sometimes we need that control, but hopefully there's a higher level option, right? And indeed, there's been a lot of work on high-level synthesis, especially on converting languages like C++ to VHDL and Verilog. This is, and this sort of imperative programming model that you have in C++ with mutable variables, loops, dynamic memory allocation, that makes a lot of sense on a CPU, but not as much sense if you're trying to design a circuit, right? So what I'd like to focus on for this talk is another approach in which we use parallel patterns from the functional programming paradigm, like map and reduce and zip and so on, in order to build up these streaming accelerators. All right, so let me explain this functional style dot product program in detail, since I'll be referring to it throughout the presentation. We have two inputs here, U and V, and these are both streams of 16-bit unsigned integers, which means that for each of these inputs, we'll be receiving one 16-bit unsigned integer per clock cycle, right? And they both have a length of 4, so I can reuse the same example inputs 1, 2, 3, 4, and 5, 6, 7, 8. So probably the first thing we want to do is we want to combine these two streams of numbers into a single stream with pairs of numbers, which we can do with this parallel pattern zip. So in this example, 1 will be paired up with 5 and 2 with 6, and so on. Next, we want to multiply each of these pairs of numbers, which we can do with this parallel pattern stream map. Stream map just applies a function, in this case multiplication, to every element of the input stream. So we should get as output from map 1 times 5, 2 times 6, 3 times 7, and 4 times 8. And then finally, we want to add up all these numbers, which we can do with the parallel pattern stream reduce. Reduce just combines a whole sequence of numbers into a single number with some sort of aggregation function, in this case, addition. So as before, the result should be 70. And there's a very natural correspondence between this sequence of parallel patterns and a 3-stage pipeline, where the first pipeline just sort of zips the two streams, the next stage does the multiplication, and the last stage performs this accumulation with an adder, right? But now you might be wondering, hey, Louis, why should we have, whoop, I jumped the gun. Or no, it's fine. Okay, no, it's fine, sorry. Yeah, so you might be wondering, hey, why do we have this register in the first pipeline? It's not in the first stage. It's not actually doing any work, right? And indeed, in prior works, like Sure, for example, you can optimize these programs built out of these parallel patterns using simple rewrite rules. So for example, let's say our language has another parallel pattern called stream map2 that's basically equivalent to zip followed by map, but it does it in a single step. Well, then in our compiler, whenever we see zip followed by map, we can rewrite it, or in other words, just replace it with a call to stream map2. And that will have the effect of combining our first two pipeline stages, which eliminates the register, right? Cool. So with this functional parallel pattern approach, there's a nice correspondence between the source code and the hardware, and the compiler can kind of optimize the programs using these simple rewrite rules. So then what's the drawback other than, I guess, people being unfamiliar maybe with these parallel patterns? Well, one drawback is that if you want your language to be useful, you need a lot of these parallel patterns, right? This is kind of a hassle. It's particularly a hassle to add new parallel patterns to your language because you need to, implement this operator in VHDL or Verilog or whatever your target language is, which is kind of a pain. You also need to explain how does this new parallel pattern interact with all the previous ones, right? How do I fuse this new one with map? How do I fuse it with zip? How do I fuse it with reduce? And so on. And also, if you think back to the previous example where we, fuse zip with map to map2, if you don't have map2 in your language, you're out of luck. You just can't implement that rewrite rule, right? So what I'm going to show in this presentation is that you can express all the operators that I listed on the previous slide with just 3 stream-related primitives, and also that this is a useful thing to do. Besides simplifying hardware generation and optimization, you actually get more resource-efficient results at the end of the day. All right, how are we going to do this? Well, we can take inspiration from prior works on array programming, which expressed array computations with just a very small IR. Specifically, there's one constructor for arrays. You can build an array of length n, where the element at index I is given by some arbitrary function f. And there's also one extractor for arrays. You can ask for the element at index I in some existing array, right? And using these 2 building blocks, you can express all kinds of higher-level operations on arrays. So for example, the ith element in the output of map is just f applied to the ith element in the input array v. And likewise, the ith element in the output of zip is just the ith element of v1 paired with the ith element of v2, right? So now I'd like to use the same idea, but for describing streaming accelerators, right? So in prior works, you've got this input language with, stream zip, stream map, stream reduce. The compiler applies rewrite rules to try to optimize this. And then prior works basically just translate this directly to a hardware description language. What I'm suggesting is that instead, we should add a new intermediate representation, a small intermediate representation, which I'm calling Siro, to this compilation pipeline. So we first lower the higher level language down to this intermediate representation, and then we apply optimization and hardware generation on the smaller IR, which is easier. And in this IR, there is, like with the array programming works, there is one constructor for streams called sbuild. There's one extractor for streams called sdata, which just gives you the next element in the stream. And there's also a mechanism for sharing a stream between multiple consumers. All right, now one more thing before I get into some examples of using this IR, I'd better clarify what kind of hardware we're trying to generate. So specifically, we're looking to generate a pipeline in which stages communicate with this handshake protocol. So every stage sends n bits of data to its consumer, along with the signal saying whether the data is currently valid. Conversely, the consumer sends back a signal saying whether it's ready to receive that data. If the consumer is not ready to receive the data yet, the producer had better not move on to the next element in the stream yet. And within each of these stages, you might want to have some internal state, like the accumulator inside of stream reduce, right? The running total. All right, let me get into some examples. So probably one of the simplest programs you can write in this IR is just building a stream of length 4 in which the output is always 42 and it's always valid, right? This expression evaluates to the stream 42, 42, 42, 42. And the hardware for it is very straightforward. You're just constantly sending the value 42 into the pipeline register. Yeah, what if you want to have some internal state in your stage? Well, we can build a stream of length 4 where the output is, instead of 42, it's I. And here I is an accumulator. It's a 2-bit unsigned integer where the initial value is 0. And the value at the next time step will be the current value of I plus 1, right? In this case, this expression will evaluate to 0, which is the initial value, 1, which is the next value, and then 2, and then 3, right? And in hardware, you'll have still the pipeline register at the output of the stage. You'll have register for the accumulator I, and you'll have an adder that increments the accumulator all the time, right? Hopefully it's OK so far. Now, let's say you want to have a stage with some inputs that reads data from another stage, right? So like stream map. Well, in that case, you can declare a producer called P. Continuing from the dot product example, we'll say that P is a stream of pairs of 16-bit unsigned integers. The stream itself can be like any stream expression. It can be an S-build expression. It can be a variable, whatever. And in this case, for stream map, we're always ready to receive the next element. The output of stream map then, again, in the dot product example where we're doing multiplication, you'll compute that by reading the data from the producer and then multiplying element 0 by element 1, right? And the output is always valid. And in hardware, what's going to happen is that the data from the producer stream is just going to be fed right into the multiplier, and the output of the multiplier will be sent to the pipeline register, right? Stream zip is very similar. In this case, you'll have 2 producers. Again, we're always ready for both of them. And the output of zip is just the data from the first producer paired with the data from the second producer, right? Now, you might be wondering, hey, Louis, why is the output always valid? And why are we always ready? Like, if one of the producers has validated but the other one doesn't, don't we have to wait? Great question. So if you're using VHDL, then indeed, you would have to take care to carefully follow the handshake protocol so as to not drop elements from one of the producers. But in the IR, you can actually kind of pretend that as soon as the ready expression value is to true, the data will arrive immediately. And then the C-hole compiler will take care to insert some extra logic in the hardware to make sure that a logical time step doesn't happen until the data is actually valid, right? Which is, I think, quite a useful abstraction. All right, one more example to put everything together. Stream reduce. So as before, we have one producer P, always ready for it. We have an accumulator for the sum. It starts at 0, and the value at the next time step is the current value of the sum plus the data from the stream, right? That's also the output of reduce. But when does reduce have valid output? Only once we've finished reading the stream, right? So we can add another accumulator I, which starts at 0, and it counts up at every step. And the output of stream reduce is only valid once I is about to hit 4, which is the length of our stream, right? In hardware, again, there will be the pipeline register. There's going to be a register for the sum. And there's going to be an adder to update the sum. And here I'm just omitting the register for I along with all the extra handshake logic that gets added for the valid and ready signals that I mentioned on the previous slide. Just for completeness, here's the full dot product example. So we've already seen 2 slides ago how to implement zip. There it is again. This is used as the input for map, which we saw 3 slides ago. And this is used as the input for reduce, which we saw on the previous slide. So nothing new here, just kind of putting everything together. All right, so we've seen how to implement these higher level, parallel patterns like zip and map and reduce in this IR. And hopefully you have some intuition about how it translates to hardware. But now what about optimization? Can we still do things like fusion, for example? And the answer is yes, otherwise I probably wouldn't have brought it up. So if I've explained myself clearly so far, hopefully you can imagine how instead of having these 2 producers pairing up their data and then multiplying them later, we can just multiply the data immediately, right? And that looks like this. Right? So 2 producers, multiply the data, there you go. And exactly as before, this will combine our first 2 stages into a single stage and get rid of the first register, which maybe we don't want. All right, now is the hardware generated by C-hole actually any good? Well, to evaluate this, I compared the C-hole compiler with 3 prior works. There's the Intel HLS compiler, which lets you write code in C++. And then there are 2 research compilers for this functional HLS. There's Sure and there's Etherling. On the x-axis, you can see various benchmarks ranging from small examples like a dot product up to larger examples like matrix-matrix multiplication, Sobel filter, image sharpening, stuff like that. And on the y-axis, you can see there are two measures of hardware quality. There's the number of adaptive logic modules that tells you, how much area is your circuit taking up, how many FPGA resources does it consume. And there's the latency, the number of clock cycles from the first input till the very last output. If we look at the latency first, you can see it's pretty much the same for every tool. So in other words, SQL is not degrading the performance in any way. And if we look at the number of ALMs, here it is for Intel HLS. Here it is for the functional HLS tools. So you can see, sometimes they're doing better than Intel HLS, sometimes they're doing a little bit worse. And here it is for SQL. You can see that in general, it's doing better than any of the prior tools. And in fact, it's really not obvious because it's on a log scale. But on average, it's actually using much fewer ALMs than the prior works, like 76% fewer than Intel HLS, 60% fewer for the other tools, which I think is kind of cool. All right, so long story short, by adding this extra IR SQL into our compilation pipeline, you can still express all the same high-level programs as you could before. It becomes easier to do hardware generation and optimization, right? Because you have a smaller language to deal with. And you actually get better, or specifically more resource-efficient results at the end of the day. If you're interested in hearing more, I encourage you to take a look at the paper. You can try the compiler for yourself. It's all open source. Or you can ask questions right now.
Yeah, the program chair taking priority, that's not good. Yeah, thanks, very nice talk. I was wondering, how does it compare to Stream HLS, like that work from Shiru Shang and Jason Kong? So they've been also working sort of DSLs for streaming applications down to HLS tools.
Yeah, oh man, I read about this a while ago, but I forget what their approach was exactly, so I'm not sure, sorry.
Yeah, so I'm wondering maybe, so their approach is similar to what like companies are doing, maybe building infrastructure with MLIR, right? Where the dot product is sort of a name operation that you know what it does.
Yeah.
And so they build optimizations from those MLIR named operations.
Yeah.
So it's a different approach, because then you have, so the IR is, say, richer because it does not encode a schedule. Like I think your IR scales encode a little bit of a way of putting things together, right?
Yeah, basically. So I guess in my approach, you can kind of simulate the IR to get, basically a cycle accurate idea of what's going on.
Whereas here is more, say, maybe declarative in a sense, right? Because you have some name operations, you have a convolution 2D with some stride, and out of there you can generate streaming-based accelerators. So I was wondering how that compares, but yeah, maybe we can take that offline.
Yeah, sure. I mean, I guess with this approach, like again, we're still starting with these sort of high-level operations, so you can, add all these, high-level things like zip and map, and you could totally add something like streamconv2D, which the programmer doesn't have to worry about how it works, and then the compiler writer takes care of implementing that. Which I guess eventually has to happen with Stream HLS as well, right?
Yeah, exactly.
Yeah,
hey, thanks for the great talk, Louis. This is Rachit from MIT. I had a question about your results. Did you measure the number of registers that you use up in your design, or is ALM, I imagine, is a measure of logic, like LUTs equivalent, essentially?
Yeah, great question. So I'm doing all this on Quartus, and my understanding is that in Quartus, an ALM includes registers and logic.
And it doesn't break down for you the logic versus register?
I think it does show the number of registers, but I didn't record that, sorry.
I see. Because traditionally, tools like Etherlink generate a lot more registers. So that's the actual trade-off they end up having. They have more registers and therefore less logic oftentimes. For your Fmax, did you pin it to 175 for all the designs, or did you do a search for the Fmax on all of the designs based on the slack you had left?
So I just used 175 in general because that's what Etherlink used for their evaluation. In general, I didn't really search very carefully, but from what I've seen, like Quartus's estimates, a lot of the designs hit, at least the, 200 plus. You know, yeah. So it's, yeah, the Fmax could definitely be better, you know, by inserting more stages and so on. But I didn't do a lot of work on that.
Understood. And the latency is wall clock time with respect to 175 megahertz and the number of cycles.
Yeah, sorry, the latency is in clock cycles.
I see. Okay. Thank you.
Yeah, sorry, maybe it wasn't clear.
Any other questions? Maybe I can have one more question, the very last question. I was very surprised because you said every operator could be represented with this syrup. So what was the most challenging operator you like to build with your syrup?
I guess one that's maybe a little bit tricky is, I don't know if I have it here. Yeah, repeat. If you want to repeat a stream, you kind of want to kind of read the whole stream into memory and then read it back out from memory. Which, yeah, I had to do a little bit of work there to get Quarters to kind of recognize the VHDL code that I generated as something that can be a memory block. But yeah, hopefully it's kind of intuitive why you can express all these operators in Sihor. Like you kind of have all the ingredients that you need, right? You can read from some other stream. You have some, you know, registers basically that can all be updated in basically arbitrary ways. In fact, fun fact, this IR is Turing complete. It's kind of cool.
Yeah, thank you.
Yeah, hopefully that answers your question.
Yeah, sure. Any more questions? Let's thank to our speaker once again, please. Our third speaker is Jung-Han Zhang from McGill University. This paper is one of the best paper candidates, so it'll be interesting. Jung-Han is going to introduce his research paper, a functional approach to synthesizing routable programmable accelerators for neural networks. And he is in the final year PhD student, and he said he's in the job market. So if you are interested, please do not hesitate to reach out to him. Whenever you're ready, floor is yours.
Sorry, the screen does not show up. Oh, okay, yes, okay. Just this. Okay, yeah, so thank you for the introduction. So I'm Zhong-Han. So today I will talk about a different approach compared to the previous talk. So we are focusing on about functional programming and high-level synthesis and with routable and programmable hardware. So our target is FPGA devices. So you may ask why FPGA? So you can see we have several accelerators like CPU, GPU, FPGA, ASIC. But for ASIC and FPGA, it's typically very efficient, especially for the power consumption, because we can customize the hardware architecture inside that. But another problem for ASIC and FPGA is they are difficult to program compared to CPU or GPU because especially for ASIC, it's a fixed architecture, and for FPGA, you need to write the HDL first to configure the FPGA. So that's a problem we want to handle now. So because FPGA is low power, low bandwidth, and it's hard to program. So basically, this is the problem we want to solve: how to program. So let's look at the example here. So we have the element as sum for 2 arrays. And this is a Python code. So this is very simple, right? We just get each element from 2 arrays one by one and sum them together. But how do we do the same thing in HDL? So this is another example. So you can see it's verbose. So we need to talk about, okay, we have a clock and we need to count the number with a register, and then we need to handle the handshaking protocol. So it's much more complex. So that's a reason HDL is more difficult to program, and people want to use high-level synthesis to generate the code instead of writing the low-level language. So a very typical method is actually especially for C-based. So there are several tools like Xilinx and Intel's tools. But these kind of tools, they can provide very simple program like this. So you can see this is a C++ example for vector addition. So, but the problem is if you fit this into their compiler directly, you will get a hardware the performance is pretty bad. That is because we need to optimize them manually. So what kind of optimization we will do is something like, okay, we need to insert the programmer to say, okay, we want pipeline here, we want to unroll here. But all these things are related to hardware architecture, so it's very low level. And another problem is usually it's very difficult to guess what's happening at the hardware level because the tool, it works like a black box, so you have no control. You cannot predict the performance very accurately. And that's one of the reasons we want to go with functional approach. So this is the previous one, as mentioned in another talk before. So we have several kind of primitives like map, reduce, and basically is to apply a function. For example, map, so apply a function to a sequence of input, and we have zip to group to array together one by one. And at this level, we don't have the information about hardware implementation. So the later stage, what we will do is we will, for example, for map, we will load it to a new IR system, and then it has more information about hardware, like, okay, data comes in a streaming way. So in the hardware, we know exactly clock cycle 0, we process the first element, clock cycle 1, we process the second element. And it probably is not good enough if we want it to be finished very fast. So we probably can further parallelize it. So we have another version like map vector. So it's basically, okay, we create several instances of function and then process it all at the same time. So we know at time 0, we just process all at once. And this is the compiler step we have. So it's also for previous work. So we have something for very algorithmic to express the algorithm only. So we don't have hardware details. So we basically use the same example for array sum. So sorry, for vector sum addition. So basically we group two arrays together, 1D array together, and then do element addition one by one. And then we will load and optimize the code, and then we get a more parallelized version. And with this, we exactly know what's happening at the hardware. So we know this clock cycle, what's happening, another clock cycle, a certain thing is happening. So that's easier for us to do cost modeling or some kind of optimization. But this is just the start of the story. So the real problem is if we have application like neural networks, how do we fit into a device like FPGA? So this is an example for VGG16. And we will start with something simple, like, okay, we look at 3 layers of land, and these 3 layers are exactly in the same shape. And we now have a device, FPGA device. And FPGA device, usually it has a limited amount of resources, and multiplier is the most expensive one. So as long as we have this amount of multipliers, and we want to feed these 3 layers into the device, then what will happen? So the most naive way is, okay, we probably reserve a certain multipliers for 1 layer. So for this example, we reserve most of the resources for layer 1, but we will run out of resources for layer 2 because we just exclude these multipliers for a certain layer. So that's not what we want. And a more ideal approach is, okay, right now we can see all these layers are less, and they use the same amount of multiplication. So why don't we just share them across all the layers together? Actually, we can squeeze these 3 layers into a single device. So this is what's going on in the prior world. So the prior world, they are using that binding to share a function and then use function code to handle each function's assets. So this is the example. So we have a function is declared at the beginning. So it's basically turn a string with an element as an input, and then output is a string of an element as well. So we have a share function f, and then usually the data comes from memory interface. So what we'll do is, and we want to call this function several times. So what will happen? So the first thing is we will have an address. We will get the address for the read data and the writing target for another address. So T1 is our writing target. So basically what we are doing is we will combine map string with read to read the data one by one, and then we will combine reduce and write to write the data one by one back to the memory. And then in the middle, we have the function code, and it just grabs the data from one source and then process it and then store the data to the destination. So this is the first function call. And if we want to call it multiple times, it will be something like this. So we we want to use the data from T1, and the partial ratio from T1 is saved to the destination T2. So you can see we read T1 again, and then do another function call and save to T2. And then we will do the same thing for the third function call and save the final result to out. So this looks simple, but what's happening in the hardware is it will be more complex, and it's the problem from the previous work. So we will talk about what will actually happen in the chip. So we have a shared function and memory interface, and then we have initial data in the memory. So for the first function call, what is happening in the chip is we will allocate the space or the resources. And these resources including this path, this blue line, and then the block that function call one, and then the reduce and map and read. All these things will occupy a space on the chip. So you can see there's a problem, because if we have multiple function calls, so it will occupy another space, and a third function call will occupy another space. So you can see it's actually scale with the number of function calls we have. And if we have something that, okay, ResNet 50, it has 50 layers, so it means we have 50 function calls, so we definitely cannot fit into device. Then how to solve this problem? So we definitely cannot go with the model with function call style. So right now we switch to a primitive actually just seen. So it's reduced. So because reduced, usually people use that to do array sum to accumulate element one by one, like this one. So basically we take an aggregation function, and it as one of input, another input is the streaming data. So right now what we want to do here is we still target at the same function, and then we want to make this reduced to iterate over different things. So it's actually the memory address we have. So like this, right now we read the base memory from the memory space, and then it actually has two parts. One is the read address, one is the write address. So we read this, and it will become a string of 3 elements, and each element contains read and write at the same time, and we will iterate over this to model the function code. So we will see what's happening later. So right now we have a reduce, and it actually accepts this instruction as the input, and then it will iterate over that. And the things here is we will need to figure out what's inside. So because basically we have a function, and then this function will accept the input read from the memory and write, and it will has a write primitive to write the data back. And then these two things, read and write, you will accept the base address from the memory. So it's similar to the instruction in CPU, but for each instruction, it will take actually several thousand cycles to process, because you know the target is convolution, fully connected, or something similar. So based with this, you can see the architecture inside the chip is much concise compared to the previous one. So we can actually make things more compact. But another problem is right now we only talk about, okay, these 3 layers are the same, but what about we want to handle 2 layers? They have different shapes. So if we look at the IR or the primitives we have, you can see if a function takes a string as the input, it has size n. It means it must all the time it must take size n. For example, 100, size 100, it must take a string of 100 all the time. It cannot take a string of 10, a string of 20, and the output is a string of 100 as well. So it's not flexible. So it also happens to the primitive like map string, so it must take a string with a fixed number. It cannot be changed. So right now, if we have 2 inputs, that the string with size 28 and the string with size 14, so it means we want to determine the size right now. If we choose the larger one, it means we need to somehow reshape the small one, like padding, we make it larger. But it means we waste the computation because these padding 14 values are actually doing nothing. And if we choose the small one, 14, as the final size, it means we need to somehow tile the larger one. But both of these are not efficient at the hardware, because it means you need to create some extra components to handle the shape. So what we want to do is to introduce a new type. So right now we only have a string type. It must handle a fixed size string. And then right now we have something new. It's called upper bounding string. So it means we just give it an upper bound, but the real string size will be determined at runtime. So it means if we determine an upper bound string with 100 elements. It means when you really run a program, it can be something between 1 to 100. So, and this is something we want to introduce to handle the issue of different shapes. So let's go back to the similar example. So right now we just make it a little bit harder. So right now you can see the function. It takes n as a string with size is as an input and output. The output shape is string with size n minus 1. So right now you can see we start to make the shape a little bit different. So what we will do first is, okay, right now because we have this new type, so we can actually make instruction more flexible. So, so first we allocate space to tell us, okay, how many instructions we want to have. So in this example, we put 3, but actually you can put 1. So you will just do one command at a time. And then what we want to do is, okay, we have a reduce, and you can see the reduce is in the map. There are new version. There are reduce upper bounding string and map upper bounding string. And what we have right now in the memory is, okay, we still have our base address, but right now we will have the new thing because this length we still have not determined the length. So at the next step, we will fill it the function. We will call the function and then feed the data from read and write the data with write. But both of them, it takes the base address, but the problem size is changed. So we also have something new. It's called uCounter. So it's an upper bounding string counter, and you will accept a number from runtime to, and this is actually the final length it will produce. Yeah. So it means, okay, sometimes we can produce n minus n size, and sometimes we can produce n minus 1. And then you can see here in the instruction encoding, we need to include this information as well. But this helps us to handle, okay, right now we have several convolution layers. The shapes, they are actually different. And then we fixed another problem for the shape, and now we still have a problem because neural network, they can have several types of layers. So in this simple example, we still have one more layer is fully connected layer, because the handle convolution layer, handle fully connected layer might be different. The optimization target will be might not be the same. So how do we handle this? So let's look at so this is something from the previous slide. So we have this architecture, we have one single function there, but right now we want to introduce a new function. So we have function 1 and function 2. So how do we handle this? So and we use a new primitive called switch apply. It's similar to switch, but it has a pool of functions and then an input with certain type, and then we have a selection signal to say, okay, which function we want to go with. And with this, we can introduce a new function. So we have function 2 and function 1, and then just wrap them out with switch apply. So switch apply now takes 2 functions, F1, F2, and then we have selection signal. So you can see here in the instruction, we have a opcode. So opcode is basically, okay, determine which branch we want to go with. So with this, we can make the accelerator to handle more than two problems at a time. And this is basically our approach. So we will show you an example about how this expression looks like in our real test case. So we want to show you the net 5 because it's simple. It's not too long. So basically, we want to write the data back to somewhere else in the memory. So we have this write address. And for the neural network, usually we have several layers, and we want to fuse that together. Like convolution layer is followed by ReLU, quantization, pooling. So the next layer, for example, we have a pooling layer, and you can see we have a switch apply here to say, okay, we want to go with identity, do nothing, or just do pooling. And you can expect the shape are different, but thanks for our upper bounding string type, then we can actually merge them together without problem. And then we have bias and quantization. So basically, it means we need to read something for bias address and then control the quantization bit width. And then we have the main computation. So it's basically, okay, we have, because convolution and the fully connected layer, they can be decomposed into something like dot product. So we have a dot product unit, and then partial sum and then to do partial sum if the layer is too large, we need to somehow tile that. And then we have the component to read the address to read the data for image and wave for convolution, and the same for the fully connected layer. And then you can see we somehow twist the readdress generator for convolution and fully connected layer is because their shape are quite different, so we need to do something more. Okay. And then we evaluate our approach on Area 10 FPGA. So we first show you the previous work. So in previous work, what they are doing is they use the lab-based sharing and use function code. So what they are trying to do is, okay, they have the convolution node VGG16, and then they synthesize it with a certain amount of DSP. DSP is a number of parallel multiplication we can allow, and GAPS is the performance number, and peak routing is the maximum routing congestion inside a chip. So you can see if they don't use they do not use too much DSP, it's routable, it can be synthesized. But if they use too many, like more than 1,000, the peak routing congestion is over 100, so it's not synthesizable. But with our approach, we can actually synthesize that with the same amount of DSP. Of course, we sacrifice something because we need to read the instruction first, so we have sacrificed something too, and the performance is a little bit lower. Okay, and for okay, I will go. And for Tiny YOLO, and another example is Tiny YOLO. For Tiny YOLO, we actually get a better performances because Tiny YOLO has a larger input size. It means each layer might have quite different sizes, and because we introduced upper boundary string, it means we can handle different shape more properly. And the next one is ResNet 50. So this is a large example we have, and we compare to against a prior work. We just want to show, okay, we can perform better than somebody also use Area 10, and then you can see if even we use different number of DSP, the maximum number of routing is not changed too much. So it means our approach is kind of scalable. And the next thing we talk in our title is programmability, because we mentioned that. So okay, sorry. Okay, yeah. So what we have is we have an accelerator, and it can support two different type of neural networks at a time, like VGG16 and VGG11. So I will jump this, and then yeah, for convolution. So conclusion, we have reduced upper boundary string and switch apply to push things together to make things programmable and routable. And then this architecture is not new, but our contribution is to express this behavior with functional IR. And that's all. Thank you.
Thank you.
Okay, and it's even a comment I have to make, not a question. So you have put in a lot of interesting work on handling these streams, but you have been mapping them to FPGAs.
Yeah.
I wonder, why have you not used devices that support these streams natively, like Xilinx's or AMD these days, Versal FPGAs, which have this array of 400 BLIW AI engines with hardwired streams between them? So I think this would be a brilliant programming approach for such a system, and it would be far more efficient than targeting FPGAs. You can run these AIEs at over 1 gigahertz.
Yeah, so this is also a problem we're facing before, is because we need to compare against different systems. For example, the system you mentioned is, I think it's suitable for this problem, and then yeah, because we start our work with FPGA, so we work with them, and we are also considering to extend them, but it needs time. So right now we are thinking about, okay, we have our Intel device, we are switching to Xilinx device, but we are still working on something that, because their interfaces are different, so we need some other work to do that. So that's the reason we don't talk about this here. Yeah,
Thank you.
But that's a very interesting point. Yeah.
Our last speaker is, he couldn't make it attending this conference in person, so he's going to deliver a talk on online, from my understanding. So it is ready?
I'm nervous.
The author is going to take the questions after the talk, and the recorded video is going to be displayed on this screen. Online, yeah, he is in online, yes.
Okay. Good afternoon, everyone. My name is Xiangyue Yang from the Institute of Automation, Chinese Academy of Sciences. Today, I am pleased to present my work, Loop Hint, a compiler-assisted loop branch predictor for embedded DSPs. Digital signal processors, known as their names, are dedicated to process digital signals. The processors are application-specific architecture. We study the stereotypical workload of digital signal processors and found that the application are highly loop-intensive. Our analysis shows that loop branch accounts for roughly 90% of misprediction in DSP kernels and more than 60% in EM bench IoT applications. Digital signal processors are utilized in real-time cases such as industrialized automation and so on, restricted by worst-case execution time, which means deterministic and agile is crucial for designing the system. So frequent pipeline flushes due to the branch misprediction is not actually acceptable. High-performance processors leverage sophisticated dynamic predictors such as tag, rely on SRAM-heavy history tables, and speculative updates aiming very small portion of irregular control flow, incurring significant power and area overhead that are often prohibitive for embedded targets. Some are even equipped with a dedicated loop predictor, specifically handle loops. However, these components require warm-up iterations, and coverage may fail to track long iteration counts or nested loop due to the table alias and capacity constraints. On the other hand, to eliminate branch overhead entirely, many architectures implement zero overhead looping. It is actually efficient, but highly restrictive. It primarily supports simple counted loops and often fails when encountering data-dependent exits, early breaks, function calls, or complex nesting due to the control flow changes. And this motivates a new solution. And we exploit compiler-known loop semantics to provide deterministic prediction without runtime learning. We actually identify for deterministic loop patterns that can be easily discovered by compiler. The first type is the constant bounded loops, is bounded by a constant number. And type 2 is invariant variable bounded loops, and it's bounded by a invariant variable. And the third type is computed invariant bounded loops, and the fourth is the memory invariant bounded loops. The figure provides concrete example of those four categories extracted from expressive DSP library and EM bench IoT benchmark. While certain benchmarks such as the convolution float 32 or the FIR float 32 are dominated by specific loop types. Other exhibits a more heterogeneous distribution. Crucially, all four categories are prevalent across evaluated workloads, and more importantly, they are statically discoverable via program analysis. This observation serves as the fundamentality for Loop Hint, a mechanism designed to extract these predictable patterns at compile time and eliminate their associated misprediction penalty in the hardware. So this leads to our system. Loop hint cross the boundary of software and hardware. It consists of 4 parts, and they are compiler analysis, loop hint ISA, encoding, hardware predictor, and the runtime update. So let's turn into the first compiler design. We use LVM, scalar evolution analysis, to identify the structured loop described above. While SCEV excels at linear transformation, it often struggles with non-linear update patterns such as bit shift. To address this, we implement a heuristic pattern matcher that inspects the loop latch block for specific shift-based induction update. Once the loop is validated as predictable, its structure comprising the loop bound, step type, and step value is encapsulated into a custom intrinsics and inserted into the preheader. The next step is to lower the intrinsics into the real instruction. To ensure that the loop hint metadata survives the backend optimization without interfering with register allocation, we defer our final instruction generation to the machine SSA stage. The transformation follows a 3-step pipeline. First is the instruction selection. The II intrinsic are initially lowered to subdued instructions. These subdued instructions act as placeholder that carry loop metadata through the early backend passes. And the second step is the machine SSA expansion and branch association. The subdued instruction is expanded into architectural loop hint instruction, which are branch style and can reuse subsequent branch lowering pipeline. These instructions are physically placed into the loop preheader. A dedicated path associate the branch-like loop hint instruction with the corresponding branch by traversing the control flow graph. The transformation is critical for calculating relative branch offsets. And the last step is the branch lowering. By reusing the standard branch lower pipeline, we ensure that loop hint instruction accurately encodes the target branch distance and extract the semantics, allowing for seemingly integration with existing hardware prediction logic. So the second part is the ISA design. We implemented loop hint by extending the custom RISC-V ISA. We proposed 2 distinctive instruction format. The first one is the loop hint branch, as is shown on the figure. It's a standard B-type RISC. The loop bound rag and the loop iter rag occupies the RS1 register and RS2 register encoding space to indicate the bound value and the initial value of the loop iter. And the 12-bit offset immediate encoding indicates its association with the corresponding branches. And the second is the loop hint step. We designed a 20-bit immediate type step val, and its compressed version CIW type 12-bit step val. This encodes the constant step value. So these are two decoupled dual instruction encoding. So if we have a severe restriction on the code size, we can use to fuse a fused single instruction encoding. This is the trade-off between the code size and the coverage flexibility. So the choice between these two kind of encoding involves a trade-off between the code density and the architectural flexibility. The fused approach minimizes the instruction count but impose the severe constraints on the branch offset and step value since they share the 12-bit immediate encoding. So we investigate the max offset and the max step value across benchmarks and found that the dual instruction encoding is more robust to EMBench IoT benchmark, and all can fit into a compressed version of encoding. As a more aggressive alternative, fused single instruction can use the coverage to trade for the perfect code size, and this is determined by the user. Now we turn into the hardware part. A lightweight loop table stores the loop bounds, iterators, tags, and prediction state, integrating with the existing branch prediction unit, sharing the same data paths and update logic to minimize hardware overhead. When a loop hint instruction is encountered, the loop predictor creates an entry in the loop table with the information encoded in the instruction. The loop predictor then uses this information to predict the outcome of the associated loop exit branch when it is fetched. As for update, when the loop iterator is automatically updated according to the step type and step value in each iteration. Another highlighted feature for this loop branch predictor is the nested loop and early break solution. The loop predictor is implemented in the stack-based LIFO structure, which naturally supports nested loop by maintaining multiple entries in the loop table, each corresponding to a specific nesting level. And early breaks are resolved through two specific scheme to ensure efficiency. The first one is the stack invalidation. If an early break targets an outer scoop, all stack entry between the current stack pointer and the matched loop tag are marked invalid, and all between the entries all between become stale. And the second approach is the age-based retirement. This is to handle the cases where loop become unreachable. Each entry incorporates an 2-bit agent counter. The counter decremented when the stack pointer resides at the entries level and refreshed upon a valid target. So experiments are conducted on Gen 5 minor CPU using expressive DSP library kernel and EMBench IoT benchmark suite, and the configuration is on the right. Loop hint, as for the result, loop hint reduces the misprediction by average 67% and often exists 98% of a reduction in misprediction in DSP kernels, especially for CONF float 32 and FIR filter float 32. Several other branch predictors are evaluated for comparison, including a simple local predictor and a more sophisticated tag-based or tag SCL configuration. in the DSP benchmarks, loop hint exhibits near perfect prediction accuracy, constantly achieving near zero MPKI values in kernels such as DSPS, FIR, or Core. In contrast, even high-end predictors like tag can report higher MPKI. The data reveals that while tag use complex history, it remains skeptical to aliasing and historyless limitation when handling long period deterministic iteration, typically of this DSP workloads. Another critical observation in the study is the comparison between loop hint and SCL variants. While tag SCL is specifically designed to handle the loop structure with its loop predictor, the results show that many highly regular benchmarks loop hint is either close to the results of tag SCL or just outperform it, but with a significantly lower hardware overhead. A potential observation regarding the result in the table is that absolute reduction in MPKI for certain benchmark appears rather small. However, in the context of embedded DSP, the relatively improvement and the shift towards determinism are far more critical than the average case performance improvements. Traditional predictors like tournament or tag rely on probabilistic history, which can lead to misprediction due to table aliasing or efficiency historyless. But loop hint, by contrast, converts this stochastic guesses into deterministic fetches by leveraging the explicit loop bounds for real-time systems. The elimination of even a single misprediction at a loop boundary.
This is the chair. Please cut to the conclusion, please. We are running out of time.
Oh, okay. In conclusion, loop hint bridges the gap between the dynamic prediction and the ZOL. Here are some highlighted features, and thank you for your attention. That's all. Is there any questions?
All right, this is Assistant Chair. Thank you for delivering a talk. We are sorry not having you in person, so we are going to take any questions from now on. Any questions from the audience? Maybe I can ask a simple question. So, for the evaluation, you said you evaluated your scheme with the hardware branch predictors like tournament, Tage predictors,
Yes.
but how did you compile such a bench publications? Did you optimize the program? Like, have you compiled the program like with O3 optimization or O2 something like that, or just compile it as it is?
The binaries is the same, but we use the different branch predictor configuration in the Gen 5 with the running with the same binary. So it's not optimized for a dedicated is not dedicated optimized for loop hint. the hint instruction in the Gym 5 is notify act as no op when the other branch predictor is configured.
Okay, yeah, thank you. Any other questions from the audience? Otherwise, we can wrap up this talk. We can thank you again. Please give another hand, please. All right.
Okay, so welcome to the very last session of the conference. There will be 3 talks in this session. The first talk will be given by Yoon Jung Kim, and it will be about MEMSPEC, memory-aware runtime for adaptive draft scheduling in speculative decoding on edge devices. Please.
Oh. Hello everyone, I'm Eun-jung Kim from the Computer Systems and AI Lab at Gyeongpoong National University. Today, I'd like to present our paper, MEMSPEC, Memory-Aware Runtime for Adaptive Draft Scheduling in Speculative Decoding on Edge Devices. Let me start with some backgrounds. Most modern large language models rely on autoregressive decoding, where tokens are generated one at a time. Since each token depends on the previous one, generating n tokens require n sequential target model execution. This sequential nature limits parallelism and becomes a major bottleneck for LLM inference. One of the most promising approaches to address this bottleneck is speculative decoding. The idea is that a lightweight draft model first proposes multiple candidate tokens, and the target model verifies them in a single execution. As a result, multiple tokens can be generated per target model execution, leading to significantly higher throughput. However, the effectiveness of speculative decoding heavily depends on the choice of draft model. Domain-specialized drafts, such as a model fine-tunes for code or math, performs well within their target domains, but often degrades on out-of-domain inputs. To quantify the impact of draft selection, we evaluated performance on JSON or in Nano. First, we compared 2 approaches, general static and Oracle statics. General static used a single general purpose draft model for every prompt. In contrast, Oracle static evaluates all candidate drafts offline and selects the best one for each prompt. Oracle static improves token acceptance by 40.3% on average. This shows that choosing the light draft model can significantly improve speculative decoding performance. More interestingly, the optimal drafts can change during generation. Oracle Dynamic, which adapts draft selection during generation, improves token acceptance by an additional 25.7% over Oracle static on average. This suggests that static selection is not sufficient. To adapt draft selection during generation, existing approaches rely on online exploration, such as multi-armed banding methods. Since the best model is not known in advance, they try different models and observe their performance. Over time, they learn which drafts works best. However, these approaches cause problems on edge devices. On edge devices, GPU memory is limited, so only a subset of draft model can reside in GPU memory. When exploration selects a non-resident draft, it must be loaded from a slower memory. On the JSON or in Nano, loading a non-resident draft takes 2.7 times longer than a single draft and verify iteration. As a result, frequent draft switching can significantly slow down generation. We evaluated MAB-based adaptive speculative decoding methods. As expected, They improved token acceptance by identifying better draft selection. However, as shown on the slides, a large fraction of execution time is spent on draft loading or fallback execution using a suboptimal draft model. As a result, the gains from better draft selection are largely offset. In other words, better draft selection does not necessarily lead to throughput on the edge devices. To summarize, dynamic draft switching can improve performance. However, on edge devices, switching costs are too high to fully realize those gains. The key problem is that the best draft may not be immediately executable if it is not resident in GPU memory. Existing methods focus on finding the best draft, but ignore whether that draft is actually available. This leads to our key insights. On edge devices, we must jointly optimize draft selection and draft availability. To address this challenge, we designed MEMSPEC around two principles. The first is proactive draft residency management. Rather than reacting after the draft is needed, MEMSPEC predicts promising drafts early and keeps them resident in best memory. This aligns draft residency with future demands. The second is decoupling draft selection from execution. Rather than blocking on non-resident drafts, MEMSPEC continues decoding with the best currently resident drafts while preparing better candidates in the background. This allows decoding to make progress without waiting for model loading. MEMSPEC implements these two principles through three components: prediction engine, draft model cache manager, and runtime controller. I'll briefly explain each component. First, the prediction engine. Instead of exploring multiple draft models online, MEMSPEC predicts the best draft model for the current context using input prompts and recently generated tokens. We implement these predictors using a lightweight BERT-based model. Second, the draft model cache manager. Based on the predictor's ranking, it keeps high-priority drafts in best memory and asynchronously pre-patches promising candidates. This helps ensure that the right drafts are available when they are needed. Finally, the runtime controller. It always learns the best available drafts while preparing better candidates in the background. As a result, decoding never has to wait for model loading. Let me walk through how MEMSPEC works at runtime. We start by learning speculative decoding with the best available drafts already resident in best memory. Meanwhile, the prediction engine analyzes the current prompts and recently generated tokens and ranks the candidate drafts. In this example, D2, D1, and D5 are the top three. Based on this ranking, the cache manager then evicts lower priority drafts and asynchronously pre-patches the top-ranked ones. Decoding continues throughout this process. Once pre-patching completes, the runtime controller switches to the better drafts at the next scheduling points. And this process repeats throughout generation. Now, let's move on the evaluation. For all experiments, we used an NVIDIA Jetson Orin Nano. For models, we used Llama 2 and Qwen 2.5 with 7 billion target models quantized to int4 using GPT-Q, and draft model around 0.5 billion parameters. We use prompts from diverse data set spanning 5 domains: general, code, math, law, and medical. We compare 5 draft selection strategies. First, general static use a single general purpose draft for all prompts. Second, Oracle static evaluates all candidate drafts offline and selects the best one for each prompt. Third, MAB Async is a state-of-the-art exploration-based approach. And fourth, Oracle Dynamic assumes perfect knowledge of the optimal draft at every scheduling point and serves as upper bound. Finally, we compare memspec against all of these baselines. This graph shows normalized throughput, where all results are normalized to general static. memspec improved throughput by 40.7% over MAB Async on average. The key reason is that memspec jointly optimized draft selection and draft residency. It not only selects better drafts, but also ensures they are resident when they are needed. Compared to Oracle Dynamic, memspec achieves 95 to 97% of its performance. This means near Oracle performance without expensive offline evaluation. To understand where the performance gaps come from, we break down execution time into 3 components: desired execution using the prepared drafts, fallback execution using a non-prepared draft, and prediction overhead from running the predictor. This graph shows execution time normalized to MAB Async. MAB Async spends nearly half of its execution time on fallback execution. However, memspec reduced this to below 5% while increasing the fraction of desired execution. Prediction overhead remains below 3.9%. This confirms our key insights. Better draft availability leads to fewer fallbacks and higher throughput. Finally, we analyzed the contribution of each component. Prediction only used the predictor without proactive pre-patching. Prediction alone improves token acceptance, but a large portion of execution time is still spent on fallback execution. Once residency management is added, fallback execution drops below 3%. This result shows that prediction alone is not enough. The key is ensuring that the predicted drafts are actually resident when they are needed. To summarize, the real bottleneck in adaptive speculative decoding on edge devices is not just selecting the right drafts, but ensuring that it is ready for execution when needed. memspec addresses both through prediction-guided residency management. As a result, it improves throughput by 40.7% over MAB Async and achieves 95 to 97% of Oracle Dynamic performance. The key takeaway is that timely draft availability is the key to realizing adaptive speculative decoding on edge devices. Thank you for your attention. I'd be happy to take any questions.
Are there any questions?
Yeah, maybe I'll ask something. Thanks for the presentation. So I was wondering, like, you evaluated this on this Llama and the other model.
Yep.
Are these traditional edge workloads? And maybe you can comment to, like, if then you execute even smaller models, how this will change? Because I guess this overhead of the availability depends largely on the size of the model, or not?
Size of draft model, target models? Or
Yeah, so you evaluated on Llama and another one, right?
Yep.
And I was wondering if those results will change if
Yep.
you use smaller. For edge devices.
Yep. Let me think for a moment.
Okay, so if there's no more questions, so let's say
In draft model, for QN, 0.5 billion model is the smallest available models, and we used similarly sized drafts for Llama. And target model,
You can take that offline.
Thank you.
Okay, thanks.
Thanks.
Thank you.
So the title of the next talk is Bridging the Memory Hotness Gap in Edge Systems with Hotness Segregated Object Allocation. And the talk will be given by Huize Wang from Peking University.
Yes.
Please.
Okay. Thank you. Good afternoon, everyone. This is Rizhe from the Peking University, and today I'm also delighted to present our work, bridging the memory hotness gap in the edge systems with hotness of segregated object allocation. This work focuses on bridging a subtle but costly mismatch in existing memory management subsystems. And this work is a collaboration between the Peking University and Huawei Technologies, and we are honored to share it at the conference. Yes, the edge systems often run with limited DRAM. So this makes memory one of the tightest resources in the real-world deployment. To use the memory more efficiently, the existing systems often use some hotness-aware approaches for optimization. Let me give you some example. The memory swapping will evict some code pages to the slow storage to reduce the memory pressure and keep the hot pages into the fast DRAM to achieve a better performance. And the memory deduplication prefers to share the code redundant pages to make more available memory and preserves the other hot huge pages untouched to keep the performance. So both of these two mechanisms are sensitive to the same issue. the kernel must know exactly know which pages are really hot and which pages are really cold. If this page information is inaccurate, then both of these two systems will suffer from performance degradation. For example, if the memory swapping wrongly evict a page to the slow storage, and the application will suffer from the extra page faults because they need to bring the page back to the DRAM from the slow storage, and as well as the corresponding expensive I/O. If the memory duplication wrongly shares the pages, and the system may incur additional overheads from the copy on write, or just losing the memory saving opportunities. However, the page hotness is not always accurate because the kernel observes the hotness as a page level granularity. But the memory objects in the same page can have very, very different access frequencies. So this is a page hotness crew, where the hot and cold objects are located in the same page at the same time. So this figure shows this pattern. The dark and light regions are interleaved in the same page instead of forming a purely hot or purely cold regions. And this makes the layout will confuse the page level classification because a page may look very, very hot even if it only contains only a few hot objects. As a result, in our micro benchmarks, these screwness can significantly degrade the memory access throughput by up to an order of magnitude. The root cause of the screwness comes from a mismatch between the system and the application, because the kernel managed memory by the page hotness, but the general purpose allocator will place objects according to their size classes. These two rules are optimized for different purposes. The kernel can only conduct page level operations through the page table. So it wants a cleaner hotness signal to achieve the page level operation. But the general purpose allocator used by the allocation prefers to use a size-segregated placement strategy to achieve a faster allocation and reduce the memory fragmentation as well. This will create the mixed pages, because the same size objects with different hotness can be placed together in the same page. But the objects with similar hotness can be scattered across different pages because their size classes are totally different. After the allocator forms this layout, the kernel has limited operations. They can only scan the page, classify the page, split the huge page, or just evade the page to the slow storage. But they cannot change the page layout of the objects inside the page because it is already determined by the allocator instead of the kernel. So our insight to address this problem is that we need to place the objects with similar hotness together instead of according to their size classes. Therefore, we present a new memory allocator, hotmalloc, with the hotness segregated allocation strategy. The hotmalloc will partition the entire heap memory into several subheaps, and each subheap will own the continuous virtual memory pages to store the objects from the one hotness class. And the object is allocated from the corresponding subheap that exactly matches its expected hotness. So with this layout, each page could become more hotness uniform. Therefore, this can reduce the page hotness crew and gives the kernel a cleaner signal for the future memory optimizations. The key challenge behind the hotmalloc is that we need this hotness information before the allocation time, that is, before the object is actually allocated and used. And we don't expect to incur too much runtime overhead. Therefore, hotmalloc uses a profile-guided optimization-based method. It will profile from the previous rounds and learns the relation between the allocation as well as the corresponding hotness. And then it will use this historical information to guide the further allocation. So there are three key components in hotmalloc. The offline analytics will learn which allocation context creates hot or cold objects, and synthesize an application-specific allocator with the hotness information inside the allocator. And during the runtime, the synthesized allocator will identify the object hotness according to their allocation context, and will allocate memory from the corresponding subheap to achieve the hotness segregation. And finally, the allocator could expose the subheap hotness directly to the kernel through our interface. So the kernel can directly use this exposed hotness information instead of just relying on some online monitoring. And the way, we could leave the expensive profiling to the could leave the expensive learning to the offline and just leave the only lightweight classification as the allocation time. During the offline phase, the hotmalloc uses profiling to collect the allocation and access information. The profile will instrument one run and tell us which allocation creates which objects and how often of each object is accessed. Then it will map the allocation context to their corresponding hotness classes. And after this analysis, the hotmalloc will generate an application-specific allocator for the deployment usage. The key point is that the profiling cost is paid before the real-world deployment. And during the normal execution, the hotmalloc does not need any online page sampling, and it also avoids the read and write barriers on the memory accesses. The learned hotness will becomes a deployment artifact for the hotness estimation instead of a runtime text. And during the runtime, the hotmalloc needs to identify the page object hotness according to the allocation context. The whole process is simple and efficient. The hotmalloc uses the calling stack frame to represent the allocation context. Yes, the calling stack frame will be encoded to generate an object ID, and the hotmalloc will use this ID to find the target subheap. And finally, after this identification, the hotmalloc will allocate memory from that subheap to achieve the allocation. We can find that the placement decision only happens once, as when the object is created. And after the placement, the object can be used normally. There is no relocation and no per-access monitoring overhead. This keeps the common memory access paths unchanged and therefore leaves the hotmalloc transparent to any applications. Based on this hotness segregated layout, the hotmalloc also provides two simplified memory management strategies for two specific scenarios. That is for the swapping and duplication. For swapping, our goal is that we need to protect the most frequently accessed objects. So we use the hot-first strategy, which groups the hottest objects into one hottest subheap, so that these pages in the hottest subheap can be more likely to stay in the DRAM even under the memory pressure. And for the duplication, the goal is totally different, because we want to find some pages that can be safely shared with low performance risk from the unnecessary and additional command write. So we use a code-first strategy, which groups the coldest objects into the coldest subheap, so that the system can just only focus on these cold pages for sharing. And other pages in the hot subheap can keep untouched to achieve a better performance. Beyond this, the allocator could also provide a simple interface to expose the subheap hotness to the kernel. For example, for each subheap between the ADDR and the ADDR plus size, the hot malloc could expose the hotness to the kernel through our newly added system call interface. This is highly useful because the allocator knows more about the object hotness distribution than the kernel, so that the kernel can cheaply directly use this information instead of just relying on some online monitoring by itself. Okay, for the evaluation, we test both memory swapping and duplication, these two scenarios. And we compare the hot malloc against the common legacy allocators, such as the one from glibc, jemalloc, and memalloc. And we will also compare the hot malloc with other hotness-aware approaches, such as memory teas from SOSP, store from the yesteryear OSDI, as well for the duplication scenario. We also compare with the SmartMD Plus that are published in TOC. Our evaluation question is very direct. We want to know if we improve the page layout, can the kernel mechanisms actually become more effective? Okay. The first result, we first checked whether the hot malloc could reduce the page hotness crew. And then in our macro benchmark, the hot malloc could reorganize the memory so that the huge page become much closer to purely hot or purely cold regions. And as a consequence, it can improve the memory access throughput by up to 7.6 times. And for the real-world applications, we also measure the maximum within-page hotness gap. That is, the different access of the most frequently accessed objects and the least frequently accessed objects in the same page. And this difference are dropped by 8 to 25 times. These results confirm that the hot malloc changes the distribution of the hot and cold objects in the memory. And as a result, the page level hotness becomes more cleaner, and so that the kernel can rely on this cleaner hotness signal for better optimization. Under the memory swapping, we found that the hot malloc improves the overall performance by up to 42.1%. The main reason of this improvement is the fewer page faults. We found that the hot malloc could reduce the page faults by up to 90%. This happens because the hot objects are grouped together in the same huge pages, and under memory pressure, the kernel can keep these pages resident and just evade other colder pages more accurately. In other words, we can more accurately evade pages, and then we therefore could reduce the unnecessary page faults. The hot malloc could also help preserve the huge page. In Linux, we found that the swapping can inevitably involve the huge page splitting, because when hot and cold objects are placed together in the same huge page, the kernel must split the entire huge page into several 4 kilobit small pages, and just evade these pages that contain the cold objects to the slow storage. And this splitting will lose the TRB benefits, and as well as incurs other additional overheads such as the TRB shutdown. Hot malloc groups some hot objects together, so it makes the huge page more stable during the execution. And as a result, the hot malloc could keeps an average huge page ratio of about 93%. The same layout principle also helps the memory duplication. With a code-first strategy, the hot malloc could group the code object together, and therefore the system can just focus on these code regions for sharing, while other huge pages can be preserved for performance. On the contrary, SmartMD Plus uses some online monitoring according to the access speed from the page table. So they need this mechanism to determine the page hotness as well as which pages to share. However, this page level classification may be misleading because of the page hotness crew. And therefore, the system will lose some memory saving opportunities. Compared to this, by giving a more cleaner page hotness, the hot malloc could deduplicate up to 40.6 times more memory, while keep the memory performance gap stay below 3%. Okay, let me conclude. The page hotness screw comes from a mismatch between the object placement and the page level kernel management. The hot malloc reduces screwness by placing objects with a similar hotness together. It uses offline profiling and the lightweight allocation time classification, as well as the simple kernel-facing interface to expose the heap hotness. And with this layout, the swapping could become more accurate, and the deduplication could save more memory. Sometimes the best system optimization is not always a more complicated policy, but could be a better interface between the different layers. So we have found that a better memory policy could start with the better memory layout. So this is the end of my presentation, and thank you for your time. And I'm happy to take your questions.
Thank you for the great talk. I was very interested in this research project. I'm wondering about the experimental setting, by the way. So you mentioned you evaluate your scheme with the MEMTIS and SOAR. Those two papers were for, from my understanding, those are for CXL memory. So do you assume this scheme may work for the embedded systems as well, or what is your evaluation setting?
Yes, we conduct our evaluation in the server. Yes, but we think our design is not platform specific. We target for the resource limited scenario, so it will also, at least it will also work in x86 platform, and at least for some other ARM platform, I think it may be work also, but I do not try it yet.
Hi. So if I understand correctly, you have one subheap for the hot objects and one subheap for the cold objects, right?
Yes.
So but like, of course, in practice, objects are not just hot or cold like binary. There's kind of a continuum, right? There's kind of a spectrum, right? So how do you decide where to draw the line, like this object is hot or this object is cold? To distinguish.
Sorry, I didn't get you.
What makes an object hot? Like, what is the...
What's the criteria to classify them?
Or like, here's a concrete example. So you look at the profile information from the last run and you say, okay, this object was accessed 100 times. Is it hot or is it cold?
Sorry?
Sorry, maybe am I talking too quickly?
Yes.
Sorry. So for you're using profile guided optimization, right?
Yes.
So the previous run, I assume you're seeing, okay, this object was accessed 100 times as an example.
Yes.
Right? So this object that was accessed 100 times, is it hot or is it cold?
Yes, we classify the hot objects and cold objects not according to its absolute access frequencies, but we will order the entire objects and find the top K objects as the hottest.
I see, and how do you choose the value of K?
Sorry.
Sorry. How do you, so you choose the top K objects are hot.
Yes.
What's the value of K?
This K could be determined by the administrative. This is
Okay,
user defined.
So it's configurable. It's configurable. You can choose what the value is.
Actually, it can be determined by the volume of the DRAM. So you need to keep the top K, the hottest object, into DRAM. Therefore, the DRAM volume could keep these objects in the memory. So we can determine the K according to these objects, the size of these objects, and find the corresponding K.
Okay, that makes sense. Thanks.
Oh, thank you.
Have you noticed some objects, if they might be cold in one part of the execution and hot in another part of the execution?
Execution.
There could be objects that start off cold, but later become hot, or vice versa.
Okay. We do not. We target for the object hotness across the entire lifetime instead of some windows within some window. Yes, we need to place some hot objects together, and to create to provide a cleaner hotness signal. So in case there actually maybe some objects maybe become cold after some time. Yes, but during the entire lifetime, it is actually hot if it is really hot. But it actually become colder at some time. But we focus on the entire lifetime. Yes.
One quick one. Maybe I missed this. This is for DRAM, right?
We do not have specific swapping method. The DRAM could also work.
All right. So I was wondering, did you notice any degradation in terms of parallelism? Like, for instance, if you pack the DRAM pages, then you would get many bank conflicts, right? So whereas if you have hot accesses across banks, then you would have more parallelism within the memory subsystem.
Yes.
Is that something that you noticed? Because you are packing the hot objects in a page, so you will reduce the amount of parallelism.
No, we need to prioritize packing other code objects. Therefore, this should be a co-design between the system and the application.
So as an example, right?
Yes.
If everything goes into one page because that's the hottest.
Yes.
Then every access will result in a bank conflict in DRAM.
These objects will be put in the DRAM and will not be compact.
Right.
I think it's time to so let's So the last talk will tell us more on the origins of indirect jumps in embedded software. And the talk will be given by Ariane Nicolas from the University of Rennes. So please go.
Sorry. Okay, do you hear me? Yes, okay. So, hello everyone. I'm Ariane Nicolas. I'm a first-year PhD student at INRIA Rennes. And today I'm going to present you the paper on the origins of indirect jumps in embedded software, which I co-authored with Isabelle Puot, Erwin Roux, and Ronan Lazerme. So, embedded software often need to provide guarantees regarding correctness, execution time, or security. Most of the time, these guarantees rely on the presence of a control flow graph of the program, which is the graph representing all possible execution paths of the program. So here you have an example of a source code and the associated CFG. So CFG is used, for example, for data flow analysis, worst case execution time estimations, or control flow integrity mechanisms. So in order to provide solid guarantees for embedded software, the control flow graph must be accurate. That means it must faithfully represent all possible execution paths and avoid infeasible edges. In a CFG, we encounter in general two types of control flow transfers. Direct jumps, whose target is statically known. So here you have an example of a direct jump in RISC-V assembly, coming from a function func1 and going to a label label1. So here the associated CFG is fully accurate because we know exactly where to go. The second type of control flow transfer is the indirect jump. So this time, the target address is stored in a register. That means it will only be determined at runtime. An indirect jump may have multiple possible destinations depending on runtime data, and its target may even be completely impossible to determine statically, for example, if depending on user input. So consequently, in the general case, constructing an accurate CFG in presence of indirect jump is impossible. So in this work, we are interested in indirect jumps' origins. We try to answer the following research question: when and why are indirect jumps generated by the compiler? Are they due to programming constructs used by the developer, or are they directly generated by the compiler, maybe without the developer knowing it? Some other questions arise also. Are there differences between binaries from different languages? What is the impact of optimization levels on indirect jump generation? So to answer these questions, we provide the two following contributions. First, a fine-grained classification of indirect jumps' origins, gathering programming constructs and compiler transformation responsible for their generation, and a systematic empirical study on indirect jump distribution in binaries from multiple programming languages compiled with two different compilers at multiple optimization levels. So before going deeper into the presentation of these contributions, I must first of all introduce the architecture we are working on, which is RISC-V. So RISC-V is an instruction set architecture which is open and extensible. We chose it because of its increasing adoption in embedded systems. So RISC-V provides 32 general purpose registers from X0 to X31. And for our work, some of these registers are relevant to know. So the 0 register is hardwired to 0. The X1 or RA register is dedicated to the return address in case of a function call. And the T0 register may be used as an alternate return address. So RISC-V provides a unique indirect jump instruction, which is JALR for jump and link register. This instruction takes as argument the return address and jump to the address contained in the RS1 register, plus or minus an offset. So depending on the value taken by its argument, this instruction may have multiple different behaviors, or 4 different behaviors, that are defined by the ABI convention of RISC-V. So if the return address is properly set, we want to come back to the calling point, so we know it's an indirect call. On the contrary, if the return address is set to 0, we want to jump without returning, it's a plain indirect jump. If the target address is the return address, then it is a function return. And finally, RISC-V provides a 4th type of indirect jump, which is generated when a direct jump cannot reach its target. Instead, a direct jump is generated, preceded by an AOIPC instruction to construct a complete address. So now that I have presented RISC-V, let's dive into our first contribution, the detailed classification of indirect jumps origins. So as said just before, RISC-V specification allows to differentiate 4 different macro categories of jump. So indirect calls, returns, long-run jumps, and indirect jumps. Some of these categories can be detailed to further refine the origin of the jump. So here is the complete classification. I will detail a few of these categories in the next part, but for now, let's focus on this big picture. So some of these categories are due to the compiler. It's the case for returns, long-run jumps, dynamic linking calls, jump tables, and tail calls. The others are due to the developer, so namely dynamic dispatch, function pointers, callbacks, and computed gotos. So now I will present 3 selected categories of jump. Jump through dynamic dispatch, long-run jumps, and jump tables. So the other categories are detailed in the paper if you are interested. So first of all, jump through dynamic dispatch. This category of jump was present in 2 of the studied languages, C++ and Rust, and is due to programming construct used by the developer. So in these 2 languages, the concept of polymorphism allows to define abstract interfaces which can be implemented by multiple concrete types. So here is a snippet of C++ code. Here we define a base class which contains 2 virtual methods, method 1 and method 2, each of them printing a small message. Then we define a derived class which inherits methods from base class, and it overrides the method 1, now printing a different message. Then we define a call method 1 function, which takes as argument a base reference. So here, the polymorphism allows to give as argument either the base class itself or any class inheriting from base. So that means we don't know which exact class will be given as argument at runtime and which exact method 1 will be called. So this is determined at runtime through dynamic dispatch and through the use of a virtual table. So for each object, the compiler will generate a virtual table, which is an array containing pointers to each declared methods. So here for a base object, we have an array pointing to method 1 and method 2. Then when a class overrides a method, the pointer will be updated to point to the new method. Here for a derived object, method 1 points to the new method 1. Then at runtime, the vtable of the object will be read, and an indirect jump will be performed to the right method. Okay, so now I'm going to present long-run jumps. So in RISC-V, we have a direct jump instruction, which is JAL, and this instruction can reach targets in a range of plus or minus 1 megabyte from the current PC. If the target is farther, the compiler must generate a long-run jump. So it takes the form of a fusion of 2 instructions, AUIPC and GALR. So AUIPC constructs the higher bits of the address, and GALR constructs the lower part of the address and performs an indirect jump. So here we can notice that even if we have an indirect jump, the address is statically known. So it is a special type of indirect jump that is specific to fixed size ISA. Now jump tables. So jump tables are generated by the compiler to optimize long comparison sequences, such as switch statements or large if-else sequences. So here you have an example of a snippet of code of a switch containing 3 cases. So a jump table is an array containing the addresses of each case code blocks of the switch. So here for this code, the following jump table is generated, pointing to the 3 cases code blocks. Then at runtime, the switch input will be used to select which case code blocks to jump to, resulting in an indirect jump. Okay, so here it is for the 3 categories I presented. Now let's go to present the second contribution, which is our quantitative study on indirect jump generation. So the objective of this empirical study is to quantify the number of indirect jumps generated in RISC-V binaries and precisely the proportion of jumps in each identified category. We want to highlight the differences between binaries from different languages and the impact of optimization levels. So I will not present the latter here because of the timing. Okay, so to obtain binaries, here is our experimental setup. As said before, we target a RISC-V architecture and precisely a RISC-V 32G architecture without compressed instruction. So we studied 4 different languages, C, C++, Fortran, and Rust. We used the Spec CPU 2017 benchmarks for C and C++ and Fortran languages, and added to it the glibc. And for Rust, we made our own small suite of benchmarks using ripgrep, core utils, and cargo. So we compiled these benchmarks using two compilers, GCC and LLVM, at 6 different optimization levels. Then, once the binary were compiled, we disassembled them and performed static analysis on the disassembled code. The idea is to, for each indirect jump instruction, to obtain its category. So we have different levels of identification. Some categories of jump can be identified directly from RISC-V ABI, depending on the value taken by the registers. So it's the case for returns and long-run jumps. Then we perform backward analysis on instruction preceding the jump to identify recognizable patterns. So at this level, we can identify calls through vtables, tail calls, and dynamic linking calls. Then, if the disassembled code doesn't give any hint on the category, we obtain the source code line using address to line, and we perform pattern matching on it. So at this level, we can identify function pointers, jump tables, and computed gotos. Then, if some jumps are left unclassified, we can perform a manual pass to identify the category manually, but this pass is optional. So here are the results we obtained after our empirical study. So on this graph are displayed benchmarks compiled using optimization level 02. So benchmarks are separated by language and ordered by size. Here are the smallest benchmarks and the largest benchmarks this way. The histogram bars represent the proportion of indirect jumps in each category over the total number of instructions. So I'm going to present the key insights on this graph. So first of all, we can see that the overall proportion of indirect jumps is quite small, only up to 8% of the instructions in Rust benchmarks. Then we can notice that smaller benchmarks exhibit less diversity in different categories of jump. This can be explained because larger benchmarks require more abstractions and thus more indirect jumps. Larger benchmarks exhibit a higher percentage of long-run jumps. This is expected because as the binaries are bigger, direct jumps are more likely to be too far from their targets and to be replaced by long-run jumps. We encountered that it's especially the case in Rust benchmarks. We encountered that it was due to its linker, which by default generates for every call a long-run jump. This can be disabled using a specific option. In C, we can see that there is quite specific systematic use of function pointers. We encountered that it was mostly function pointers stored in structures to serve as methods for the structs. And in C++, we can see that there is a wide use of dynamic dispatch calls, which is expected also because of the object-oriented paradigm of the C++. Okay, so here it is for our results. I will now conclude and open on future works. So I presented here our work on the origins of indirect jumps. We provided 2 contributions, a complete classification of indirect jumps origins and statistics on the number of indirect jumps generated in each category in RISC-V binaries. So now that we have identified the different categories of indirect jumps, future works could focus on how to manage them in embedded software. So development guidelines could be formulated to discourage the use of certain programming patterns or to encourage the use of specific compilation options to remove some categories of indirect jumps. And to go even further, a more radical approach could think about entirely removing the indirect jump instruction from an ISA and providing compiler and hardware support to efficiently replace them with safer constructs. So this is the approach that I will be exploring during my thesis. So thank you for your attention. Feel free to ask a question.
Are there any questions?
Yeah, hi, thanks for the talk. kind of a small question. So when you say tail calls in the paper, I guess you mean as in like tail call optimization?
Yes, tail call optimization, yes.
Why does that lead to indirect jumps? I would have expected it to be basically like, you know, a while loop where you just kind of jump back to the beginning of the function each time.
A tail call is, I mean, at the beginning it was supposed to be an indirect call at the end of a function, but it is replaced by a jump because it's the last instruction of the function. So you don't need to return to the calling point. It's only a jump which is performed. Does it answer your question?
But then in that case, there would be no indirect jump at the end of the day, right? Or
no, the call at the beginning was supposed to be an indirect call. So it's replaced by an indirect jump instead of a call.
I think the question is, if it's a tail call, there shouldn't be. It should be a direct jump and not an indirect one.
Yes, but the indirect jumps are generated only when the last instruction was supposed to be an indirect call and not a direct call. A direct jump will be generated as a tail call, as an optimization, if the call at the beginning was a direct call. But here it's indirect calls that are optimized as indirect jumps.
Okay, thanks.
Okay.
Yeah, about the radical.
Yeah.
Go back to one slide, right?
Yes.
So I think removing the instruction is quite radical, but
yeah.
You could still enforce compilers to generate zero constructs, or you could, like, instead of going and finding that in the assembly,
yes.
like for instance the switch case thing. So there's a lot of cases where the compiler could produce
something
extra
else.
debug information, something because what the interest is to be able to reconstruct more accurate CFGs.
Yes, exactly.
So if this information is known by the compiler, because it is known, so this can be passed somehow, so that the control flow graph can be more accurately produced.
Yes, but there are some kinds of indirect jumps that are more difficult to replace with something else.
Yeah, no, that part I know, but I'm saying that you could increase the accuracy of the control flow.
Yes, of course. That's why there could be development guidelines to.
No, but with the compiler as well.
Okay.
So the compiler could help out in.
Yeah, yes. The compiler itself could.
Hi. Thanks for this analysis. Two questions. First of all, C++ supports Lambda. Did that appear at all in this analysis at all?
So we used the spec CPU 2017, and we encountered that there were no Lambda at this point. But I think, yes, it would be an indirect jump.
Okay. Other question is, Rust has function blocks a lot like Lambdas, and they use them a lot. I guess those show up in the analysis.
Yes, you can read the paper if you want, but yes, but this kind of jump, it depends if they are under a trait, if they are given as argument, like you speak about closures, that's it. Right. Yes, closures can result in an indirect jumps if they are given as argument in a function.
Thank you.
In your presentation, you only use 32-bit instructions. Have you looked at applications with different bit widths? Like 64 bits, 128 bits?
I think 64 instead of 32?
Yeah.
I think it normally doesn't change anything. It's only the addressing that changes.
But it would be interesting to see whether the analysis you have done would be
maybe.
The same or would become different.
Yes, for example.
Yeah, for
yeah.
example.
I have a question as well. So you mentioned you are using a static analysis.
Yes.
Could you tell us why you need you need to perform the analysis at the source code and at the binary level as well? So why do you need both, and what do you do with this analysis?
We wanted at the beginning to do only static analysis on the binary, but it was we were missing information, so we continue at the source code level. We could have used only the source code maybe, but yes, it was also to see if some specific patterns were generated in the assembly. So both were interesting for us.
Okay, so let's thank our speaker again.
Don't leave.
Good. Final talk of the day, a quick closing session. Yeah. So let's hope that you guys enjoy the program. I think it was pretty cool. Big thanks to the presenters. I think we're pretty much on time. I think there were only 2 people that overshot. So most of the speakers were really great on the timing. So thanks a lot for that. There was something that I already announced in the opening, is that we decided to give Distinguished Reviewer Awards. And so we have selected these 2 TPC members. Only, let me fetch the right one. Yeah, only, so I'll ask JJ maybe to come also in front for the picture taking. So yeah, the recipients were Klaus Schneider and Jungkook Choi. So let's give them a hand, both of them. And since Jungkook is here, so maybe we can do this physically. Klaus will receive his award. So maybe you can just take it. So yeah, congratulations first of all.
Oh, thank you.
And thanks for the service. So take this, maybe stay in the middle. Is that okay with the light in the back? Maybe let's do something. Let's do this. Right. All right. Yeah, great. Thank you. Thank you. All right. We also said that we had narrowed down the selection for the Best Paper Award to these 2 candidates. That was based on the reviewers' comment, the discussion within Hot Crap system. Then we had some extra reviewers check those 6 papers that we selected, and we got a ranking, but we wanted to wait for the conference to then decide on the final winner. And the winner is towards verifiable system code using a DSL. So big congrats. We actually have one for each author. So you can pose, and maybe you take all of them. And yeah, should I do this again? Yeah, congratulations.
Thank you.
Right, thank you. Yeah, congrats.
Thank you.
Yeah, thank you. Congrats. All right, and that's it. So thanks for attending LCTES 2026. As I said before, thanks to the authors for submitting, for the speakers for sticking to the time, to the session chairs, which did an excellent job moderating, steering committee members, and of course the attendees. I think it was a very nice conference. No ill-intended questions and questions from the audience. So thanks a lot. And yeah, see you next year. We don't know yet where, somewhere in the globe. So I wanted to have a picture, but of course we cannot take that out from the PLDI organizers. They should announce that. All right, thank you very much. Enjoy the rest of the afternoon. Yeah.
I want to record that this, my thanks to Geronimo and Christian for a fantastically conducted PC meeting. Thanks to JJ and the rest of the steering committee for making this a wonderful conference. I've been on many program committees. I've chaired conferences. I think I learned a lot during the program committee meeting.
It was very efficient, right? It was like
you were very efficient and you were very I think the kind of questions that were discussed in the PC meeting was really very good. I also would encourage all the people here and your contacts, your 6 degrees of connection, to submit next year to LCTES.
Yeah, great comment. That was not rehearsed, so thank you. Yeah.
So I would, on behalf of the steering committee, I would like to thank the program committee and also Genomics for the events. If we plan to organize LCTES next year as a 2 full-day event.
All right. Yeah.
And if you have any feedbacks or any suggestions, welcome to reach me. We would like to have the LCTES being still part of PLDI, but with more activities, not only the presentations from the authors. We would also like to include further events.
Maybe a panel. Yeah. Right.
So we would like to also hear your opinions. Welcome to talk to me or write me a mail or message if you want to. Yeah. And thanks a lot for attending the conference. Hope to see you next year somewhere in the field.